Safety moment number 14. Don't believe everything you see, especially level gauges. They can be very, very deceptive, and they can be cause of significant serious accidents. Improper level gauge reading in the 3 Mile Island plant was part of the cause of the partial meltdown of the nuclear reactor at 3 Mile Island. Now, here's a picture of a vessel, and it's connected to a gauge glass where you could see a liquid level and the vapor size connected to the top. Now, typically we would expect this level to be the same as that level, but I'm showing it's not. Why is it not the same level? Well, is the density of this fluid the same as the density of this fluid? It may not be. And here's one of the reasons. This fluid may be a very hot vessel. This is a long tube, and this fluid is a cold vessel. So being cold, this fluid is more dense than this fluid. And even though it's the same exact fluid, let's say it's water, this could be a boiler, and you're reading the boiler temperature, and this could be colder water on the outside. Now, this boiler, if it has bubbles of air in it, it may be less dense than this liquid level. This liquid level might show like up here. So you're not reading the actual level. Now, most times it won't matter too much because if you're off by a ½ inch or so on a 12-inch gauge, it's not really all that important if you're trying to keep 6 inches, whether you have 5½ inches or 6½ inches. But it is a phenomenon that you need to be aware of. Also, let's say this was a water gauge, a water level gauge. What about the debris and corrosion that ends up in this tube? Are the valves open? Was this serviced and the valves opened? You want to make sure that these valves are opened as well and not plugged. You have blow-offs that allow you to check that, but this is important that these gauges work properly. Now, on some of these gauges, there may also be alarms. So let's say you have a floating magnet in here, and you have a ring around here that will sense where that magnet is, or it could be a magnet on the outside with a metal disc inside, some means of sensing this level, and that can be triggered to an ESD, emergency shutdown, or some other device. And this could be a level controller. But understanding this phenomena is important. What could go wrong? The density of the liquid in the glass is different from the density in the vessel. Really? How could that happen? Well, the liquid in the glass might be cold and denser, or the vessel liquid may be entrained with vapor bubbles, making it much less dense. Foam might be in the vessel. This is very common in amine systems where, let's say in the amine absorber, you have a foam level on top of your liquid level. Well, that's certainly going to give you a false reading. Valves might be closed or plugged with debris. Ask anyone who worked at 3 Mile Island about wrong level readings, and they will give you an earful. We'll continue on what could go wrong. Debris could be in your sensing lines. The sensing lines may have an air liquid trapped somewhere in the line. If transducers are used, a whole host of reasons can give you an error. A transducer is a device that converts pressure into a voltage, typically 0 to 10 volts, or into an amperage, typically 4 to 20 milliamp. But a transducer can add a host of reasons that can give you an error. Fluids might be supercritical. Well, if the fluid is supercritical, you're not going to get any difference in density between the liquid and vapor. So level controllers just won't operate because the density of the liquid and the density of the vapor are the same. There is no actual liquid and vapor. There's just a supercritical fluid. Freezing or boiling of the sensing lines is a concern. Ask anyone who worked at the Texas City refinery about wrong level readings, and we'll show you what happened at the Texas City refinery. I mentioned foam layers. Now, typically on a amine absorber, you'll have the ability to skim off the top layer, and if there's foam, they'd be able to skim off some of the foam along with the top layer. But foam can certainly distort your actual reading. In this case, what is the level that we want to know is L2, but it's showing higher than L2 because of a foam layer that's here. So having a foam layer can certainly distort your readings. And what my goal here is to show you the phenomena. So if you get strange readings, you can start investigating as to see why. Now this type of a foam layer, this height of a foam layer, which is over the top tap, can really add confusion to what your actual level is, because you see now your top gauge has a head layer of foam on top of it as well. So not only is this number distorted, but this pressure is also distorted. So having a very high foam layer can make it even more tricky to determine the actual level within that within that. Adding electronics can make things even worse. So here's our typical level gauge, and what we had here before was a glass that somebody had to read, or a glass that we then put a magnetic disc in and a sensor on the outside of the glass, and that sent back information to the control room. Now we're going to put in a transducer that's going to look at the differential pressure between this point and this point, which should correspond to the differential pressure between here and here. But when you add a transducer and a transmitter, you now have a level transmitter, which typically operates at 4 to 20 milliamp signal, and it's very dependent upon who set it up. Now, let's say he or she instrument person set this up to measure the difference in head of oil, and the liquid that's in here is water amine. Well, this is not going to be calibrated correctly if it's set up for oil. And let's say the water amine concentration is different than what this is set up for. Let's say it was set up for water amine, but of a different concentration. Again, the sensor is not going to give you the right information. So adding electronics doesn't always help. It just adds a convenient means of getting this information from here to the control room, but it has to be set up properly. Now, does the operator know whether it's set up properly? No, it's the instrument person that knows. So that's where now is another layer of personnel that have to be trained properly and make sure that they have used the right instruments and the right calibration. Not only that, but these also have to be calibrated for zero offset and span, which is something we'll talk about more. So adding electronics did help us with communicating to the control room, but it may have added even more errors to our actual reading. If you add foam on top of that, you even increase the errors more. So now what we have is a foam layer that's causing an error, plus the potential for a personnel error in calibrating this sensor that could add error, and now that information is sent to the control room, and the control room operator is making judgment calls based on information that could be flawed. Another method of using electronics to indicate the level in a vessel would be to put a transducer on both taps. Transducer on the top tap, a transducer on the bottom tap, taking the electronic signal that comes off these transducers and converting it to a 4 to 20 milliamp signal that goes to control center. Now you may wonder why we use a 4 to 20 milliamp signal and not a 0 to 20 milliamp signal? Well, being that a 4 shows for 0 level and a 20 shows for maximum scale level is a very good way of being certain that the equipment is actually working. Because let's say this was broken and you ended up with a 0 reading, you might think you're at 0 level when in fact you could be at some high level. So a 0 level or 0 milliampere signal will tell you that there's a fault. Something is wrong with the system because it's not showing any signal at all. So it could be a break in your wiring. It could be a bad connection or something else. But the 4 represents 0 level. 12 would be 50% level because the difference between 4 and 20 is 16. So 8, which is half of 16 plus 4 gives you 12 milliamp would be 50% scale, and then 20 milliamp would be full scale. And that's just another method of using electronics to tell you what the level is. But it does not get rid of the problem of foam layer, especially if that foam layer is higher than the top tap that's shown here. Again, I'm showing you now a foam layer that is even higher, yet it's above this second tap. So now we have a double problem related to foam. The fact that the foam is impacting this pressure as well as this pressure, and that complicated by the fact that the instrument person has to calibrate this correctly, and now the operator is dealing with an even more complex set of phenomena that may be giving a false reading. Calibration errors can be a significant problem. Let us say that you have, this is 6 foot here, from here to here, and you're maintaining, you're in the control room maintaining 5 foot, but in actuality, the level is 6 foot. Now, you don't know it's 6 foot, so you think you still have another foot before you get to this point. Well, this can certainly give you a significant concern. On the next slide, we'll show you why. Remember in the earlier slide when the level was at 6 foot and showed at 5 foot here? Well, if that same vessel now had 26 foot of head, it would still be reading 5 foot level here. The operator would be thinking that the level's at 5 foot, and this becomes 26 foot, 27 foot, overflows the vessel, and you have a catastrophe. That is what happened at the Texas City refinery. There are many, many types of calibration errors that you need to be concerned about. One of them is shown here, calibration for the wrong fluid. So I set up my equipment, I set it up perfectly to measure the fluid level, and I'm setting it up for water when I'm really measuring is water glycol. So there's an error right there. And if you don't catch that error, it can carry on for years as the same maintenance person comes and calibrates the same piece of equipment for the wrong fluid. Calibration for the correct fluid, but different density. Let's say it's calibrated for a fluid that's at ambient temperature when the fluid is actually at 200 degrees Fahrenheit. And that would be density difference due to temperature. Zero offset error is a very serious error because, well, not only did that happen in the Texas City refinery, but it gives you a false sense of security, especially if your liquid is over the top level. So if, let's say, as in the Texas City refinery, it's reading 5 foot level and it's really 6 foot level or 26 foot level, you wouldn't really know the difference. Then there's span calibration error. Is that 50% when you're getting 12 milliamps? Is that really a 50%? So it's got to be calibrated across the span, all the way from 0 up to 0, which would be 4 milliamps, up to 100% level, which would be your 20 milliamp. And then you could have a programming error, which is the operator puts in the wrong factors that are associated with programming the equipment, or the use of the wrong range transducer. Imagine using a 0 to 100 psi transducer on a tap that's only going to see 0 to 5 psi. So that would certainly be an error in the setup of the instrumentation. Typically, for a critical measurement, we use a 2 out of 3 voting, which helps, but it does not help if all 3 of them are wrong. So if all 3 of them are calibrated for the wrong fluid, it's certainly not going to help you. But with a 2 out of 3 voting, what you can do is you have 3 signals coming in. Try to get your 3 there. 3 signals coming in, and if you see that 2 of them agree, you accept those 2 and you can ignore the third and have an instrument person check out that third to see why it's not reading properly. This voting does no good if all 3 are equally wrong. If all 3 are set up for the wrong fluid, that's certainly not going to help you. But it does give you some level of confidence in your reading if 2 out of the 3 are giving you the same reading. Ideally, you'll have all 3 out of 3 giving you the same reading. If the same instrument person makes the same error 3 times, that's not going to afford you any protection. All 3 devices are out of service, like with the story with the NRAPs. That's not going to give you any sense of confidence either. Compensation not made for density. Well, if that's not being done, all 3 of them will be reading wrong. So 2 out of 3 voting is helpful, but it has its limitations. Summary. Realize that gauge readings that report to your central control center may be wrong. Always use your best judgment to access parameters. I remember one time where a control board operator was at the board tapping the gauge, and wondering why it was pinned, and not realizing that if he would have stepped back, he would have seen that all the gauges were pinned. The system was overpressurizing. For instance, if you are filling a vessel with a maximum level gauge of 6 feet and you keep filling it and it reads 5 feet, even though you're continuously filling the vessel, suspect that something is wrong. If you're continuing to fill and it's staying at 5-foot level and your maximum is 6 foot, well, that tells you that you're filling it, you know you're putting liquid into it or fluid into it, and the gauge is not moving. You probably have a 0 offset error in your reading. You may want to halt the filling and have an instrument person check out the instrumentation. Further, you may need to check a tap above the gauge to ensure that the liquid is not above the upper gauge level. That would typically be done by your outside operator. In continuing the summary, evaluate the consequences of a wrong level measurement and act towards the safest mode of operation. Be cognizant that if the fluid being measured changes in density, it will impact your level reading unless a density compensating device is incorporated into the electronics. Make safety and reliability your highest priority. Your job is to understand the shortcomings of the data you get and to make the best decisions. At the beginning of this safety moment, I mentioned 2 very serious incidents that were caused by wrong level data. At least in part were caused by wrong level data that was being sent to the plant operators in the control rooms. If you have the time, check out the 3 Mile Island accident. Even better, watch the CSB, that's Chemical Safety Board video on the Texas City Refinery accident. I give you a link below that you can use to see this accident or this accident investigation. It is very compelling. And in fact, when it first came out, I said to myself, someone got hold of the information that I've been training on and put it into an accident report on the Texas City refinery. I had not known about the Texas City refinery, but all of the cautions that I had given to plant operators were like compacted into this one safety accident report. It was things like too much overtime, men being fatigued, lack of communication, improper instrumentation readings, a attitude of casualness with regard to safety and operations, people being overworked, covering too many plants at one time, and on and on. Safety moment number 15. Horseplay has no place in your plan. Prank was played on a sub-foreman. Somebody spun the gauge on him. The sub-foreman was doing a high-pressure boiler hydro test, and it was going to be a test at 1500 psi. So he used a 2000 psi pressure gauge to do the test. Somebody pranked him and spun the gauge so that when the gauge was reading 0, it was really up to 2000 psi. So he kept pumping water into the boiler, and eventually it started reading. And when it got up to around 1000 psi, which was well beyond what the boiler was rated for, because the test was going to be at 1500 psi, and the 2000 plus 1000, he was already up to 3000 psi. The boiler started leaking at the tube connections to the steam drum and the mud drum. What was happening was the steam drum and the mud drum were actually yielding and stretching. And once that happens, the boiler is a piece of junk because it can no longer be trusted to operate at high pressure. This was a high pressure steam boiler making 600-pound steam, and I think the production rate was somewhere in the order of 300,000 pounds per hour. So it was a large size boiler that was effectively destroyed in that one test. Now the sub-foreman was suspended. The prankster was fired. The plant was shut down for over a year. It went through the entire operating season unable to operate. And one of the things there were a couple of things that were wrong here. First of all, hydro tests should always be done with calibrated gauges, so that false or that damaged gauge would have never seen that test had it been calibrated and then brought to the test site. Also, secondly, you have to have at least two separate gauges. Ideally, one a chart recording gauge and the other one a dial gauge, so that you're knowing, and it's connected at two separate locations on the boiler and set up at different locations. And it's typical for a test like this to have an instrument person there or someone from the chem lab with a dead weight tester to confirm that these readings are correct. Because don't forget, this is a critical piece of equipment, and it's certainly a safety hazard if in fact one of those tubes had ruptured or ripped out of the steam bundle. It could have sent shrapnel across and hurt someone or even killed someone. The result of what did happen was that the piece of equipment was totally destroyed. Sub-foreman was suspended. The prankster was fired. There are a lot of people who are pressing for the sub-foreman to be fired as well. I defended the sub-foreman because he was uh, he was certainly one of our best employees and just was lacking in some some basic training that should have been provided before he did this pressure test. Safety moment number 16, rigging and outrigging support cautions. Riggers must be qualified by classroom training and by on-the-job training. And by on-the-job training, I caution you, it's not by somebody who already has bad rigging habits. It's by someone who is truly qualified and understands the theory as well as the practice of acceptable rigging procedures. Rigging accidents can injure employees, can result in death, can destroy plant components and plants. I'll give you two examples that I have firsthand knowledge of. Adequate size crane was ordered for a lift. Outriggers were placed on soft soil. The tube bundle was about 60 feet above the grade, connected to the crane. This is a tube bundle for a heat exchanger. The tube bundle was unbolted and removed from the heat exchanger. Once the full weight of the tube bundle was supported by the crane, the outrigger sank into the soft soil. The tube bundle and the crane top crashed into the plant and hung up on the structural steel at about 40 feet above grade. The rigger claimed the hydraulic hose failed and caused the accident, and there was hydraulic fluid on the floor next to the crane. It's only many years after the fact that I wonder if someone might have cut the hydraulic hose after the crane did its crash. I'll never know that, but there needed to be a reason for this crane to topple. Uh, Obviously, being that the outrigger dug into the soil well over as the crane tipped over, tells me that there was not enough dunnage or enough support under the outrigger. Whether the hydraulic hose actually broke or not, no one can really tell me that. But that's one accident that occurred. Fortunately, no one was hurt. Fortunately, there was no major plant damage. Another crane was brought in and hooked up to the load and lifted the load off safely, uprighted the crane that had toppled, and that job was completed without further incident. Accident number two. There was a long lead time vault that was delivered to the facility. This was a precast concrete vault which had a lot of rebar in it, and it had two openings, one on each side, which was for piping to come through the vault. And the piping had been cut by an acetylene torch, so it was a sharp edge opening in the vault. The unloading rigger failed to inspect the cable for capacity. He had used the cable many times, failed to inspect the cable for wear, failed to protect the cable from the sharp edges where the cable went through the vault openings and were up against the acetylene torched pipe that came through each end of the vault, and that acetylene torched edge was a sharp edge where the cable made a sharp 90-degree turn across the as it came out of the vault and then went up to the crane. The lift was made, and all he was doing was taking this vault off the truck. He lifted the vault up. The truck moved out, and before he could move the load and put the load back on the ground, the cable snapped and the vault was destroyed. The vault was now just a piece of junk because it had all cracks in it, and it was all even to remove the vault became difficult because it was all bound together by reinforcing rods, and it was just a piece of junk, worthless to the job. Worse was that the job itself was delayed, and it was an important job for the company, and we had to get that new vault made or remade, and then that lead time had to go through the extended lead time again to get a new vault in order to complete the job. Lessons learned. Just because something did not fail yesterday does not mean it will not fail today. Proper rigging checklists should be followed regardless of the size of the job. A rigger should always confirm the rating and condition of his or her cables, and should never allow sharp edges to press against the cable being used to make the lift. Ground conditions need to be evaluated, and if cribbing or outrigging pads are needed, they should be used. In this case, in these two cases, the rigger certainly needed additional training. So training is extremely important. I want to go back up to item 1 that's shown here and says just because it did not fail yesterday does not mean it will not fail today. How many times have you heard an operator say or a maintenance person say, we always do it this way, we've never had a problem, even after you've questioned some of the technical reasons why perhaps you should not do it that way. Perhaps there's a risk associated with doing that way. And I can give you 2 examples. Let's take for one the explosion that occurred in a liquefaction plant in Plymouth. I think the state was Washington State, but it was in Plymouth. I know that was the town. And what happened was in the plant itself, in the pre-treatment system for the liquefier, there was an explosion and shrapnel and was sent into the LNG tank and punctured holes in the LNG tank and also broke a small pipe containing LNG, which then spewed LNG out. And it was a serious situation for a while because no one realized if the inner tank had been punctured or not. There were certainly holes in the outer tank. Well, that purging procedure that was used had been used for years. It was a normal purging procedure. It was a pressure purging process. It was not fully evaluated properly, and although it hadn't failed in prior times, it failed. There was a source of ignition, and it ended up causing this damage and gave the industry a black eye as well. So just because it didn't fail yesterday does not mean it will not fail today. Is a caution that I always give operators and maintenance personnel. If there's any risk associated with the job, it should be evaluated. And even if it's been done 100 times before, how many explosions does it take to hurt you? Only one. The lessons that we can take from this safety moment are that when hydraulics are used to hold outriggers in place, the hydraulic hoses must be inspected, and the operator must ensure that the pressure under full load does not exceed the rating for the hoses. For instance, the hose has a certain pressure to lift the crane up, but once you put the load on, that hose is going to see additional pressure as the outrigger, if it's being secured by hydraulics, will we have now not only the crane load, but the load that's being lifted. Now, a lot of outriggers and most of the larger ones are fixed outriggers where they have screw jacks and they're not dependent upon hydraulics. But sometimes lifts are made where hydraulics are used, and this needs to be taken into account. Riggers and crane operators need to be properly trained and approved as qualified before performing their job functions. Theirs is probably one of the most important functions on the job because if you drop the lift, there could be people injured as well as equipment damaged. Safety moment number 17, cybersecurity. A comprehensive summary of Hack Against U.S. is Grave Threat Cybersecurity Agency Says by Ben Fox of AP. Now, this report was summarized by AI. Hackers inserted malicious code into routine update of software. Homeland Security, Department of Treasury, and other federal agencies were compromised. The breach of security went undetected for months. Experts determined it could take years to understand the full ramifications of this breach. And this reflects things that have happened in the gas industry. There have been soft targets that have been cyber attacked whereby they've asked for ransom or they have opened and closed gas valves that should not have been opened and closed, and these may be the precursor to a larger attack that's yet to come. But there is cyber security concerns right now in the gas industry as well as in government as well as in any part of the energy industry. In the cyber attack that was mentioned that happened against the federal government. Attackers embedded their malware into legitimate software updates. So it was a sneaky way to get into the system. They didn't go directly against the computer systems. They inserted their malware into updates for the software that was being used on those computers. The attackers extracted sensitive data for months. They made their malware mimic the normal software and use behaviors to avoid detection. The attack was attributed to Russia in that particular attack, but that is only as credible as the source of the report released. The attack was deemed to be very sophisticated by infiltrating trusted vendor software. That breach in security had profound implications for the U.S. national security. It exposed weaknesses in the cybersecurity infrastructure of the federal agencies and highlighted the risks posed by the over-reliance on external software vendors. Think about what happens when you have a consultant. You may have multiple firewalls on your computer systems, and then you hire a consultant and you share with that consultant your confidential information so the consultant can work on it. Well, what are the protections that your consultant has for his email server, for his computer systems? So he has your sensitive information now, he or she, and may not have the same level of cybersecurity that you have on your main system. Many natural gas and other energy sector cyber infiltrations have been experienced since that government cyber attack. Some are concerned these early attacks are being used to understand the energy sector's weak points for a much larger future attack. After that major cyber attack on the U.S. government, Cybersecurity and Infrastructure Security Agency reforms were made. Cybersecurity and Infrastructure Security is called CISA. Increased funding for CISA was enacted, enhancing the resources and authority of the CISA to enable it to respond more effectively to future threats. Improved supply chain security, establishing standards for best practices for securing software supply chains and reducing the risk of similar attacks. Enhanced public-private collaboration, encouraging greater cooperation between government agencies and private companies to share information and coordinate responses. A zero trust architecture was adopted, adopting a zero trust approach to cybersecurity where access is strictly limited and all activities are continuously monitored and verified. Lessons learned are as follows. The need for proactive defense. Reactive measures are insufficient against sophisticated attackers. Organizations must adopt proactive strategies to detect and mitigate threats before they cause harm. In this case, the horse was out of the barn. Many months of carrying that malware within the government agencies leaked a lot of sensitive information. The importance of threat intelligence. Timely and accurate threat intelligence is critical for identifying and responding to cyber attacks. Enhanced information sharing between public and private sector is essential. Value of redundancies. Building redundancies into critical systems can help mitigate breaches, impact, and ensure operations continuity. The necessity of international cooperation. Cyber threats are a global challenge that require international collaboration to establish norms, share intelligence, and hold bad actors accountable. Safety moment number 18. Expect components to fail. In one plant, it was the practice at this plant to swing from one steam turbine driven pump to the other steam turbine-driven pump every shift. So every 8 hours, one pump was shut down, the other pump was started up. And they would switch every shift from one turbine to the other turbine. The procedure was to start the pump that was not online, to start that pump up, and then to shut down the other pump so that the pump that was just put online would take the load. Now, the pump that was taken offline would automatically stop pumping and the flow would try to go backwards through the pump. However, there was a check valve that would prevent that from happening. At least that's the way it was designed. When the flow on the pump being taken offline tried to reverse due to it being shut off, the check valve would shut and the pump would have no flow. That's the way it was designed, and that's the way it worked for many years, until that fateful day when the check valve stuck in the open position. The pump being taken offline started to spin backwards, overspeeding the turbine in reverse. The turbine blew apart as 6 workers dove for cover. Fortunately, no one was killed or injured. It actually failed. A different design of the system could have avoided this event. That's item number 1. The procedure did not consider this event. That's layer number 2. That was a failure in planning, and thus did not have precautionary actions in place. The check valve that got stuck in the open position, that's what failed open. There was a reverse clutch on this turbine that would not allow it to spin in reverse. But for many years it had never operated and the maintenance on it was lacking. Well, this clutch was intended to prevent this very such accident from happening. If the turbine ever tried to go in reverse, it would lock the turbine in position and not allow it to spin in reverse. But that failed to kick in when the turbine spun in reverse. And then there was a lack of training for the personnel. No one ever thought of, what if the check valve gets stuck in the open position and the pump actually acts as a prime mover to spin the turbine backward? The lessons learned are: expect components to fail. Build into the design and the procedures means and methods to avoid such catastrophic events. Train personnel to be aware of any such actions. This event had not been emphasized in the training. All similar components in the plant need to be hazard. That means the hazards need to be evaluated and documented. And you need to put in place layers of protection. Certainly, maintenance was lacking on this particular reverse clutch, and this accident should not have happened. When the site was visited after the event, there were turbine blades everywhere, sticking out of the insulation and other components in the plant. The shaft of the turbine, which was about 4 inches in diameter, was blown out of the turbine casing and bent like a pretzel. It was a catastrophic type of accident, and fortunately, the 6 employees who ducked for cover, none of them were injured other than having quite a fright. Safety moment number 19. Understand combustion. There are 3 significant hazards associated with LNG. One is asphyxiation. LNG vapor is essentially methane, and if you get enough of it, it displaces oxygen, and you can be asphyxiated by a cloud of bog that does not have a sufficient oxygen to sustain life. 2, it's cold. You can have freeze burns, hypothermia, embrittlement of metal, a vapor collapse in a tank when you spray LNG into a tank and the vapor that's in the tank is warm. There are a number of associated hazards with it being cold. Burns are certainly one of them. A cold liquid burn can not only damage skin and cause a burn, but it can also, in one case, the person was killed as a valve burst open and LNG splashed onto the person, and the person was killed. I myself had a vapor, not a vapor, it was a freeze burn on my finger at one time. I was making up a fitting, and I knew it was. I had gloves on, and I knew that I could feel that it was the leaking vapor and liquid was freezing me, but I made the fitting up, then took the glove off and looked at my finger, and it looked very strange. And eventually it started getting palish, then blackish, and I didn't want to, but I then went to a doctor, and the doctor said, "Well, it's going to take a while for this to heal, but you're lucky that it only impinged on one side of your finger, because if it was both sides of the finger, it could have been much more serious." This safety moment will focus on methane in air mixtures being flammable. Oh, that's the third item that I did not mention, and that's that the vapors of LNG are flammable when mixed in the correct mixture with oxygen, and oxygen is in air. This safety moment will focus on methane in air mixtures as being flammable. Three things are required for a flammable substance to burn: oxygen, fuel, and heat. Take away any one of those three, and the fire does not progress, does not propagate further. So if you take away the oxygen, the fire goes out. If you take away the fuel, the fire goes out. If you take away the heat, the fire goes out. And that's three ways of fighting a fire, is by taking away one of those: the oxygen, the fuel, or the heat. This is just a mental graphic for you to place somewhere in your mind and have this picture in your mind that the anatomy of a fire requires these three components: the oxygen, the fuel, and the heat. And then you could have either a fire or an explosion, a deflagration or a detonation, depending upon the confinement of the fuel gas mixture. Let's talk for a moment about how flame propagates. Now, I can have a room that is filled with, let's say, 3% methane in air. Strike a match, and the match will glow and then extinguish. Why did the room not explode? We'll talk about why. Or I can have a room that's filled with 25% gas and air. And I might have trouble breathing in that because now I've depleted some of the oxygen content of the room. But I strike a match, and again, the flame does not propagate away from the match. It glows and then extinguishes. Why did that flame not propagate throughout the room? Well, if I'm somewhere between 5% and 15% and I strike a match, kada boom, the room blows up. Why? Because I'm within the flammable range of that fuel. For methane, it happens to be between 5 and 15%. For hydrogen, it's much broader. For acetylene, it's something like, I don't know the exact number, maybe 4 to 80% uh, fuel and air mixture. It's a very wide flammability range. We'll probably see that on one of the slides yet to come. Why does it not burn when it's too lean? Well, it's because when combustion takes place, in this case, I'm going to combust a CH4 molecule. You can see it's one carbon atom with 4 hydrogen atoms. And that's where it gets its molecular weight of 16. Carbon has a molecular weight of 12. Hydrogen has a molecular weight of 1. So 12 plus 4 gives me 16. There's my molecular weight of methane. And if when that combines with 2 molecules of O2, now O2 is a molecule that is connected together as a diatomic molecule. You'll always find oxygen as diatomic. That means 2 atoms bound together. So I got a molecule of oxygen here and another molecule of oxygen here. And when these combine with one molecule of methane, in a complete combustion process, I end up making one molecule of CO2. This is carbon with 2 oxygen atoms and 2 molecules of water vapor. Now, you might not see the water vapor coming off of a flame, but there is water vapor, but it's as vapor, not as liquid. Now, when you start your car engine on a cold day, you'll see water dripping out of the back of the exhaust pipe. Where's that water coming from? Well, that's this H2O that came out of the combustion, and then it hit the cold tailpipe, and it cooled down and became a liquid, and that starts dripping out the back of your tailpipe. As your exhaust system heats up, it leaves the car as a vapor, and that's why you'll see cars on the road that have just been started up and you'll see a white vapor coming out of the tailpipe. Well, that's the steam that's coming off of your combustion process. As it heats up further, it comes out even hotter steam, so you don't see it visibly condensing at your tailpipe. But at any rate, that is your process that takes place, and it is an exothermic process. Exo, exit, meaning heat leaves the process. So as that process takes place, heat leaves the process. Now, in order for this process to start, you need to reach the activation energy or temperature in order to start this combustion to make the process happen. So if this does not get hot enough, it'll never have this process take place. So let's say I have this set of molecules combine to produce this set of molecules, and the heat that's leaving reaches the next set of molecules, and they in turn combine and produce heat, and they in turn reach the next set of molecules. Well, there you have a process where the flame is propagating, and that's what happens when you're between 5 and 15% fuel and air. But when you put an insulation barrier between this set of molecules and this set of molecules, there's not enough heat to reach this set of molecules to cause it to combust. And that's what happens if you have too much air in the room. The air acts as an insulator. So although the fuel air that went into the match flame burned, it never propagated past the match to get into this next set of molecules. Now, what about if you have too much fuel in the room? Well, the too much fuel can also act as an insulation barrier to prevent this heat from getting to the next set of molecules that are ready to combust. So these molecules do not reach their activation temperature required to cause the chemical reaction to take place. So too much fuel or too much air acts as an insulator and prevents combustion. That's why if you want to purge out a tank, you put in nitrogen. Well, that nitrogen makes much less oxygen available for the combustion, and also the nitrogen acts as a insulation barrier, so you end up having the process not propagate, and you end up having a safe condition. Let's look at that graphically as we move along. Here's a graphical representation of the fuel gas mixture in a room. Let's say I have a room and it's filled with 100% air. Well, I got 21% oxygen. As I start to add gas to that room, the oxygen content decreases because I'm now mixing the air in the room with a certain amount of fuel. In this case, I'm mixing methane. I get up to 4%, and I'm still not at a point where ignition will take place. There's too much air in the room for ignition to take place. And let's say I started off and the room had only 16% oxygen when I started. Well, now as I add fuel, I'm getting even more difficult to burn. And when I get to the flammable limit, now this flammable limit looks to be about 7%. Here it was 5%, now it's 7%. Well, let's follow this line where we started. We start off a room, we get up to 5% gas and air, we have an explosive mixture. Get up to 15%, we have an explosive mixture. Anywhere between this 5 and 15% gas and air, we have an explosive mixture. This lower level is called the LEL, lower explosive limit. This upper level is called the UEL, upper explosive limit. And in between is the flammable range. Now that flammable range gets smaller and smaller as you have less oxygen in the environment. So let's say I started with a room that was at 16% oxygen content, and I go up in this direction, and my flammable range now starts at around 7% gas in that room's environment. I keep going up and I'm going on an angle. I get to maybe 11.5%, and that's my new flammable range. If I start off with a vessel that's been purged and there's only 9% oxygen in the room and I start to add gas, what happens is I never go into that flammable range. So this zone here has been purged out sufficiently, so I never go into a flammable range. Now, when you're dealing with piping and you purge out piping, you typically bring the piping all the way down to almost 0% oxygen because it's very easy to purge out a pipe. You put nitrogen in one end, stuff that comes out the other end is originally 100%. Let's say you had gas in that pipe, 100% gas, and then all of a sudden, or you had air in the pipe, and then all of a sudden you get down, your oxygen content in the pipe drops 16 to 12%, 8, 4, almost zero, down to what is essentially zero, and you say, okay, that pipe is purged. And that's easy to do with a pipe, especially a small pipe. But let's say now you're dealing with a tank that happens to be 200-foot radius, and I'm talking about the largest LNG tanks that are in existence. And I don't think they're quite 200-foot radius, but they could very well be 150-foot radius in size. Those are about 4 BCF tanks. So you put that, you can't bring it down to zero because it would take you an excessive amount of nitrogen to do that. So you're safe enough if you're following the AGA guidelines for purging. You're safe enough if you bring it down to 9%. There's actually, I would go to the AGA purging guideline and use their value for what is the safest, what is the safe value. I'm using 9%. I gave myself a little extra cushion, more than the AGA safety guidelines. And then as you add gas to the tank, you never go through the explosive limit or through the flammable zone. One of the things that you have to watch out when you're purging large tanks is that you don't have channel purging, which means that your purge gas goes up in a channel and you're reading the outlet as being purged well enough, let's say down to 9% oxygen, but there are pockets within the tank that might have 11, 12% oxygen. You want to make sure that that doesn't occur, and there are different ways to do that. Let me just talk for a moment about exhausting a large tank from that's filled with gas and you want to purge that large tank out. Typically, you have vents that are used, and you have a vent on the top of the tank, a large vent on the top of the tank, might be 16-inch in diameter. You'll have vents all around the annular space, and it's quite common for contractors to put on a plastic tube extending that pipe up to the top. One caution I give you is that gas going through plastic causes static electricity, and you do not want a source of static electric charge causing a spark. So what is common practice is, or recent common practice, is to put a wire mesh or wire cable around that plastic to take the discharge off of that and ground it to the tank. Whether that's sufficient to get rid of all the static electricity is unknown, but it's certainly a safety measure that I've seen taken in some cases. I've already mentioned purging, and I'll go over that again just on this slide to emphasize the fact that once you get the content of the vessel below a certain concentration, and I go in accordance with the AGA guidelines, then you can introduce gas into that vessel without the concern of reaching the flammability zone. Now, keep in mind, this is temperature dependent. Remember when we spoke before about that insulation barrier that's going to prevent the next set of molecules from reaching the ignition temperature? Well, it does not reach the ignition temperature because there's that insulation barrier between what was just burned and what's next to burn. But what that assumes that you start off at ambient conditions. Let's say you're already at 900 degrees Fahrenheit. Well, then your whole flammable zone is totally different than what's shown here because now you're already at conditions that are very near the ignition point of natural gas temperature. So that insulation barrier does a lot less assistance in preventing a flame propagation from occurring. So this profile that I'm showing you here is really intended for atmospheric conditions. And this was the table I was talking about earlier, and I mentioned hydrogen and acetylene as having a very wide flammability range. And I didn't know the exact numbers, but I'm showing them here. Hydrogen is from 4% all the way up to 75%. So I can have 75% hydrogen in 25% air and have it ignite. Now, hydrogen is a fuel that you have to be very careful about because hydrogen has a very low activation temperature or very low energy level required to ignite it. So hydrogen leaks. If you have, let's say, pure hydrogen leaking, the static electric charge of that leakage alone might be enough to cause it to auto-ignite. So hydrogen is a, a gas to be certainly concerned about. Carbon monoxide has a very wide range of flammability as well. However, carbon monoxide, the major concern with that is the toxicity of carbon monoxide. It has a high affinity to be absorbed by your hemoglobin. So if you breathe in carbon monoxide, not only does the hemoglobin grab onto it, but it does not want to release it. So even though you've been exposed to carbon monoxide and then were brought out to fresh air, you may experience carbon monoxide poisoning for many hours after you've been brought out into a pure air environment. Methane, about roughly 5 to 15%. Acetylene is a concern where it's a very wide range of 2.5 to 81% gas and air flammability. And I'll give you an accident that I know happened. In fact, I visited the two employees that were injured on this accident. They were welders, and their habit was to have the acetylene torch in the side truck door compartment of their truck. And if you know of utility trucks, they have very very heavy steel side doors on their back compartment of the truck. And they'd have the acetylene tank inside the bed of the truck, the hose going through a hole in the side of the truck going into the cabinet, and the hose and the torch was in there. And the welder just cut a piece of pipe, shut the hoses on the torch, put it in the cabinet in the containment on the side of the truck, closed the truck door, and started grinding the pipe. A spark from the grinder went near the truck cabinet. The truck door blew off, hit one welder in the arm, ripped his muscle out of his arm, hit the other welder in the leg, ripped the muscle out of his leg, and then hit a steel door, dented the door. Both of these employees were disabled. I remember visiting them at their houses, and they did not come back to full-time work. They were then permanently, partially disabled. And it was a very unfortunate accident, but it's something that we had a lessons learned from. And what did they do wrong? One, putting the torch into a confined space, uh, and they did not shut off the tanks to make sure that the gas was fully shut off. Obviously the valve on the acetylene torch itself had some leakage, and that's how the acetylene accumulated in the cabinet on the truck. So let's test ourselves on what we just learned. Let's say I have a mixture of 10% methane and 19% oxygen. Let's look at where that is on this chart. Okay, 10% methane is here. 19% oxygen is here. Will this blow up? Yes, it will. We're right smack in the almost stoichiometric position of the flammable zone. And stoichiometric means that you have exactly the right amount of oxygen to fully consume the fuel that you have available. Let's say I had 10% methane and 9% oxygen. Well, now I'm over here. So will that explode? No, it will not, because I'm in the non-flammable range. Let's say I had 20% methane, so I'm up here, and 19% oxygen. That puts me out to here. Will I have an explosion? No, I'm too rich. Let's say I had 3% methane, so I'm down here. And I could tell without even looking at whatever the oxygen content is. 20% oxygen, too lean to burn. How about 10% methane and 5% oxygen? 10% methane, 5% oxygen. I will not burn. I'm in the non-flammable range. The learnings from this is that your job as LNG engineers is to ensure that combustible gas mixtures do not occur where they are not designed to exist. Indeed, they do and should exist inside a boiler. Combustible mixtures do exist and burn intentionally in a boiler. At the air inlet to boilers, in the US, there's always a gas detector that's required by code. At the Skeekta plant in Algeria, there was no gas detector and combustible gases were sucked into the boiler, which overfired the boiler and caused the boiler to explode. See the next slide. As can be seen, the results of the Skeekta incident were catastrophic, at least in this part of the plant. Safety moment number 20. I'm going to talk about understanding tank pressure and differential pressure. All gauges are differential pressure gauges. We don't commonly think of it that way because we commonly think if you go get a pressure gauge that reads 0, you put it on a pipe and you read it, and it reads 20 psi, and you think that it's reading the pressure that's in the vessel or the pipe that you're measuring. Well, actually, what's happening is it's giving you a pressure differential between pressure that's in the pipe and pressure that is measured on by a barometer. It's measuring with the 0 point calibrated to be 1 atmosphere. So if you get a 600-pound gauge, that really doesn't matter because in a 600-pound gauge, it's going to read 600 pounds regardless of what the barometer is positioned at. In other words, the barometer might say that the outward pressure of the atmosphere is 14.7 pounds per square inch, or it's 15.2 pounds per square inch, or it's 14.2 pounds per square inch. That's your barometer pressure. But when you're reading 600 psi, that differential, that small amount, is not visible to the eye. So we often think of a gauge as being reading absolute pressure, but it's not. When you put your pressure gauge on your tire in your car and you read 32 psi, that's above atmospheric pressure. That's reading a differential pressure. Now with high pressures, doesn't matter. The barometer changes only within typically a pound to a pound and a half maximum variation in that order of magnitude. But when you start to measure pressures in very low pressure vessels meaning like an LNG tank that might operate at about 1 psi differential pressure, as your barometer changes, so does that differential pressure, and quite significantly. So if I'm reading a tank pressure, I'm really reading the difference between the absolute pressure inside the tank and the absolute pressure outside the tank. And a lot of people don't understand that, including many LNG operators because they're used to just reading the tank pressure, and they say we have a pound 1 psi in the tank pressure today. The bog pressure in the tank is 1 psi, and when I say bog, that means boil off gas. And let me talk about that. Before I go into that in more detail, I want to talk about how tanks are constructed. There are single containment, double containment, and full containment tanks as shown to the left. A single containment tank has a inner shell of 9% nickel steel. I'm pointing that out here. And an outer shell of carbon steel. Now that's the most common type of single containment tank. And then a far distance away, you'll have a dike. When I say a far distance away, I'm not talking about 5 to 10 feet, but I'm talking about significant distance away. You have a dike, and that is in case there were to be a spill. Let's say that inner tank were to rupture. Well, the outer tank, being carbon steel, would immediately rupture as well because it's carbon steel, and the LNG would be contained by this secondary containment. But this is called a single containment tank. A double containment tank is one where you bring the secondary containment real close to the tank. Maybe it's only 5 feet or 10 feet away from the tank, and it's really close. So when your inner tank fails, the outer tank also fails, but the LNG is contained in this close encounter or close proximity outer dike. And what you do is you'll have vapor leaving, but the liquid will be fully contained. Up in the single containment tank, you have a tremendous amount of vapor leaving because you have a high surface area that's in contact with the LNG. And in the double containment tank, you have a much smaller surface area. Then you have a full containment tank, which is a inner tank of typically 9% nickel steel. And when I say 9% nickel steel, it could also be certain alloys of aluminum instead of 9% nickel steel. The ones I'm most familiar with are 9% nickel steel, although I've done jobs that involve aluminum tanks instead of 9% nickel steel. But for the majority of the tanks that I've come across in my career, they've been 9% nickel steel, and the newer tanks are almost solely 9% nickel steel. In a full containment tank, you have a secondary containment, which is typically a concrete vault that the entire tank is in, and the concrete vault might have a layer of stainless steel or cryogenic material on the side of the tank as well, on the inside of the tank as well, that acts as a cryogenic barrier. But the containment is actually this outer tank. So if there is a breach in the inner tank, what will happen is the outer tank will hold back not only the LNG, but also the vapor. So in a full containment tank, if you had a failure of the inner tank, neither the liquid nor the vapor would be spilled outside of the outer tank. In the double containment tank, the vapor releases to the atmosphere. In the single containment tank, the vapor releases to the atmosphere. Now, this tank that's shown here is a special kind of tank. There aren't too many of this type of tank, in that you see there's a special breather tank here. In this tank, there's an annular space that's filled with nitrogen. And this breather is nothing more than a bladder with a weight on top of it that allows that barometer change to keep this nitrogen pressure at a fixed differential between the barometer and the annular space. Now, look at these single containment, double containment, and full containment tanks that I show here. The annular space is filled with boil-off gas. And inside this annular space would be insulation. And we'll talk in more detail about how much insulation and what kind of insulation is used there. Get a better understanding of this differential pressure, I'm using this graphic that's shown here. I have a person in a spacesuit, and he's in outer space. And there's pressure in outer space, the absolute pressure is 0. So the spacesuit is experienced 16 psi, and the differential pressure between the pressure in the spacesuit and the outside environment is 16 psi differential pressure. Let's say the person in the spacesuit still is maintained at 16 psi absolute, and the person is on the top of Mount Everest. Top of Mount Everest, the pressure is only 4.4 psi absolute, so the differential pressure is 11.6 psi differential. Let's say the person is at 16 psi absolute. Again, I'm keeping it constant, this internal pressure of the spacesuit. But you're on Earth and you're at sea level. Let's say the barometer is reading 14.7 psi absolute for your pressure of one atmosphere. Well, then the differential pressure would be 1.3 psi absolute. So if you imagine, let's say this was a tank, well, I'd be measuring a differential pressure. I'd say the pressure in my tank is 1.3 psi over the barometer. So it's really 16 psi absolute is the pressure that's being read. Let's say I go to the lowest recorded eye of a hurricane, and the pressure outside is 12.8 psi absolute, but the pressure in the spacesuit is maintained at 16 psi absolute. The differential pressure is 3.2 psi differential. Let's say one last thing: the highest recorded barometer, 15.7 psi absolute. Spacesuit is at 16 psi absolute. The differential pressure is only 0.3 psi differential. Let's do the same exact thing, but now we're going to use an LNG tank. And the LNG tank we're going to see is being maintained here at 16 psi absolute with a differential pressure 1.3 psi differential. So my barometer is 14.7. Now what I've done for this example is I'm going to maintain the differential as a constant pressure. So now if the barometer drops to 12.8, means my absolute temperature, my absolute pressure I should say, has to drop to 14.1. And if the barometer raises up to 15.7, then my absolute pressure inside the tank has to raise up to 17 psi absolute. Those were all done in order to keep this differential pressure constant. Now here's where I want to point out the saturated temperature and pressure. What is the temperature of your LNG? Temperature of your LNG is dependent upon the pressure that the LNG is stored at. In this particular case, it's 16 psi absolute, which for I use methane as the gas, as the LNG. It equates to a temperature of minus 256.8 degrees Fahrenheit. This is a lower pressure, so I would expect to have a colder temperature. And look at this, it is much colder. This temperature is minus 259.6 degrees Fahrenheit. And here I'm at a much higher pressure, so what I would expect is that my temperature would be warmer. And in fact, the temperature is warm. It's only minus 255.4 degrees Fahrenheit. So you might ask, where did I get these numbers from? Well, I used the software that was developed by the National Institute of Science and Technology. The software is called RefProp. And since we're dealing with saturation points, all I need to do is input one piece of data. In this case, I put in the absolute pressure. And whenever you're dealing with software, that's thermodynamic software, you deal with absolute pressure because that's the scale that it's designed to operate at. Now you can use gauge pressure, but you have to put in a correction factor then to tell it what your barometer is. But if you go with absolute pressure, it can tell you right away what your saturated temperature is associated with that absolute pressure. It could also tell you what your liquid density is, what your vapor density is, what your liquid enthalpy is, vapor enthalpy, liquid entropy, vapor entropy, and it can tell you many, many more properties of that fluid, depending upon which ones you selected to populate or which one you selected to investigate. In this case, I selected only density, enthalpy, and entropy, and temperature. So with that, I'm showing for 16 psi absolute, minus 256.79. Now, what happens if I increase that pressure? Well, if I increase the pressure, the temperature is going to get warmer. If the temperature gets warmer, what's going to happen to my density? My density is going to drop. Why will it drop? Because it's going to expand. That liquid is going to expand. And density is the amount of mass per unit volume. So here I see a density of 26.272. I go to a warmer temperature, the liquid expands, my density drops to 26.202. Let's say I now go to a pressure of 14.1. That's a very low pressure. So what I would expect is my temperature to get colder. And as my temperature gets colder, this volume is going to shrink in size. As it shrinks in size, my density is going to increase because the density is the mass per unit volume. And next thing I want to talk about is how we measure gas. We measure gas in the gas industry by what's called a standard cubic foot. And it's a cubic foot, which is a 12 inches by 12 inches by 12 inches, and it's at standard conditions. Now, there's nothing too much standard about standard conditions because different industries use different standards. The gas industry, using AGA numbers, would use 60 degrees Fahrenheit and 14.73 psi absolute, which gives me a density of a standard cubic foot of gas of being 0.042457. And this is, again, I'm using pure methane. Now, LNG would not be pure methane, but it's mostly methane, so that's why I chose to use pure methane for this example. Now, what does Henry Hub use? Henry Hub uses 59 degrees Fahrenheit and 14.73. How about your EPC contractor that builds your LNG plant? Well, they use 14.696 psi absolute and 60 degrees Fahrenheit. So when I say standard temperature and pressure, it really is important to know what industry you're dealing with. Now, it really doesn't matter too much if you're dealing in small quantities of LNG, but let's say you're dealing with a shipload of LNG that contains somewhere between 30 and 60 million dollars worth of LNG. Well, you want to make sure that you're using the correct standard conditions when measuring that LNG so you don't end up getting shorted, even if it's by a very small fraction of a percent, times that by $50 million, and you have a significant amount of money. And if you're dealing with, let's say, 100 ships a year, it can be quite a significant difference. So understanding when you're dealing with contracts that you're dealing with an overseas vendor and that you're buying the gas from, you need to make sure you do your accounting properly so that you do not use the wrong standard conditions. So you might think about, well, we're really buying energy. So you think about a BTU. A BTU is the amount of heat that is required to raise 1 pound of water 1 degree Fahrenheit. But a BTU is not an accurate measure either because I didn't say what the temperature of that water is. Some people use 39 degrees. I say some people, I'll say some industries use 39 degrees as the temperature of the water. So the specific heat of that water is different, 32 degrees as it is at 60 degrees, as it is at 69 degrees, or whatever temperature that you happen to be using. So the term standard cubic foot may not be standard. The term BTU may not be accurate unless you define what limits what temperature you're looking at the water at, and using water as the BTU measurement because you're raising it 1 degree Fahrenheit. The calories also has the same problem measurement. The only really accurate measurement of energy is the joule, which is a Newton meter. Press 1 Newton of force against 1 meter distance, that's a joule. And that'll be an accurate measure, and that's the most accurate measure that you'd want to target for measuring your energy when you're dealing with LNG in high quantities. So what does all this have to do about safety? Well, let's say you are the operator in an LNG plant, and this is your barometer that's shown here. This is your barometer, and you know that in 2 days from now, you're going to have a hurricane. Well, what accompanies a hurricane? A low pressure, low barometer. So you know a hurricane is coming, and 2 days before you start pumping out more and more vapor from your tank space. You want to get that tank pressure way down so that when you get to the hurricane, this differential pressure does not end up blowing your relief valves and causing you to vent gas to the atmosphere. So you as an operator or as the engineer overseeing these operators has to know that your barometer projections for the next few days are increasing barometer, decreasing barometer, so that you can add some smarts to how you operate your boil-off compressors. And keep in mind, as you lower the tank pressure, your liquid is going to get colder and colder, which means it's going to boil off more rapidly. So it's not as easy as I'll just turn on the boil-off compressors and they'll bring the pressure down. As you bring the pressure down, it takes a significant period of time to get the pressure down because as you're dragging the pressure down, more boil-off is being generated. So in summary, your job as an engineer that's leading a group of operators is to anticipate barometer changes, to adjust your bog removal amounts accordingly, i.e. if a hurricane is coming in tomorrow, then start today, bring those pressures down in the tank and avoid blowing relief valves. Failing to preempt barometer changes can cause hazardous conditions as well as result in a costly loss of bog inventory. The moment number 21, frost heave. I call it the silent destroyer. Under tanks containing fluids that are below 32 degrees Fahrenheit, if the tank is in contact with the ground can freeze and ice lenses can form. Ice lenses continue to grow, building one on top of the other, and move upward with tremendous amount of force. They can lift buildings, they can lift tanks, and they can lift them unevenly because they may form one place and not in another, and that can cause a tank leak. So you want to make sure that you don't have frost lenses building up, ice lenses building up underneath your tank. And we'll talk about how those are avoided. Such heaving can grow until there is damages done to the bottom of the tank, and you want to avoid that. And the very same thing can happen to pumps or pipes that are underground and operating below 32 degrees Fahrenheit for an extended period of time. Let's talk about how a typical LNG tank, and this happens to be a single containment tank, how a single containment tank is constructed. And the reason why I picked the single containment tank is because it's the most popular type of tank that is in the United States. There are roughly 100 to 110 LNG plants in the United States, and some of them have multiple tanks. Many of them have this type of construction of tank. And although I've made this a very generic tank, I've shown duplicate ways of doing things on this one picture. But let's take a look at this and get an idea how this tank is built. The inner tank is either aluminum or 9% nickel steel, and the floor is a thinner 9% nickel steel. Why is the floor thinner? Because you don't have to have deal with the hoop stresses that are associated with this outer tank. Down at the bottom of the tank is about 18 psi as far as the pressure on inside this from the liquid head, 18 psi, maybe 20 psi. It depends on the height of the liquid, and you have to design for that hoop stress. So here it might be an inch, inch and a quarter thick nickel steel, 9% nickel steel, and up here it might be only a ½ inch or 5/8, something a lot thinner up here than what's down here. The bottom, typically only a quarter of an inch. It's just there to give you a floor because it's being supported directly by the floor underneath it. So it's not seeing any real stress, but it has to be a leakage barrier. And in this tank, you have LNG, and the LNG is continuously circulating around the tank. These are convective currents. Now, no one really knows the velocities currents. I've heard it said to be in the order of magnitude of 1 foot per second, but I won't say that as a fact, just as a hearsay. But there is continuous circulation, and if there isn't, then you have stratification, which we've already spoken about. And this continuous circulation means that the temperature here is approximately the same as the temperature here. So this is saturated LNG, and this is subcooled LNG. And you need subcooled LNG to feed your pumps. And there's two methods of feeding pumps. You can have an external pump, which is here, and which would require a bottom penetration to your tank. So this would be feeding external pumps. They're external to the tank. And you have a bottom penetration. Bottom penetrations are a concern. Bottom penetrations are a concern only because if you get a leak in let's say this joint here, there's no way to shut off that LNG. You have to de-inventory the tank and then make that repair. However, if you have a newer tank that has a bottom penetration, they're equipped with internal tank valves, which allow you to shut the tank via this internal tank valve that's operated from the top of the tank. And it's operated, of course, either pneumatically or hydraulically from the top of the tank so that this valve can operate. And if you get an emergency shutdown, it would be typical for this valve to shut down depending upon the type of emergency shutdown. Now, how do you fill the tanks? Well, let's say before we fill the tank, let's talk about another type of pump that's common to tanks, and that's an internal tank pump. And internal tank pumps are installed in a tube that goes from the top of the tank down to the bottom of the tank, and it has what's called a foot valve on the bottom, so that when the pump is lowered, it opens the foot valve. When you remove the pump, it closes the foot valve. And these internal pumps can be turned on electrically. There's an electric wire that goes up to the top, and it pressurizes this tube, and then a pipe is connected from this tube to your vaporizers, and from there the LNG is pumped to the vaporizer. Typically for internal pumps, you'd have 4 tubes, 1 of them empty, 3 of them with a pump, and that's typical. It doesn't mean that it has to be 4 with 3 pumps, but it's a typical configuration that you'd find. Let's say you want to fill the tank. Well, let's say it does not have these top this method of withdrawing liquid from the tank. So you want to fill the tank, you want to do a bottom fill, you can come in through your bottom penetration. You want to do a top fill, you come in and hit a splash pan and put the liquid layer on top. That's the most common configuration of older tanks. Newer tanks are configured without this bottom penetration. Most of them are. You can still buy it with a bottom penetration if you so desire, but most of the newer tanks are consisting of these tubes that are coming down with the internal tank pumps. But then how do you bottom fill if you don't have a bottom penetration? You bottom fill by way of having a pipe that comes down to the bottom. Do the bottom fill. Your LNG comes in here, comes into this funnel type of configuration, and the LNG is delivered to the bottom of the tank. Now, This is very common, and only in recent years has they realized that this can become problematic. Because let's say you're filling a very light LNG into the tank. Where do you want to put a light LNG? You want to put it on the bottom. This way it mixes with the heavy LNG that's higher up. So if you have a light LNG, you want to put it on the bottom. But let's say it's very light LNG. Well, light LNG means there's a very light or low density head here, low density fluid in here, which causes a higher head required to get to the same pressure as the liquid that's out here. So you can have, let's say, a liquid that's up at this point here, giving you the same pressure as a liquid that's over here. And this could be as much as 5-foot difference. So what happens as this liquid level gets higher, this funnel starts to overflow and you're really doing a top fill at the last stage of your filling of the tank when you want to be doing a bottom fill. This is a relatively new problem that is being addressed in different methods, but it's one that is certainly a phenomena that you have to consider when you're doing bottom filling with this configuration of tank. Now, we spoke about the inside of the tank, and this particular tank happens to be the way most tanks are, with a breather on top, and it's not typically a single breather, but multiple breathers on top. This is a suspended deck. This is suspended from the roof, and on top of that suspended deck is typically perlite insulation, and you see that perlite goes down the annular space as well. Now, the blue layer that's shown here is fiberglass. And why would they want fiberglass insulation in here alongside the perlite? It's typically about a foot thick of fiberglass. And the reason is because the tank, when you cool it down, shrinks in size. It shrinks, a large tank will shrink about 6 inches in diameter, in size. And as it does that, this perlite drops down and compacts. And then if you have to recommission that tank, you have to warm up the tank. Let's say you need to do a repair. For instance, let's say one of these straps has a little leak associated with it. So now you have to decommission the tank in order to make that repair. So if you have to make that repair, you have to warm up the tank. When you warm up the tank is going to grow 6 inches. Same way when you cool it down, it shrank 6 inches. When you warm it up, it's going to grow. If this was all perlite, it would be a solid mass, and something would have to give. Either the outer tank would have to yield, or the inner tank would buckle. And you don't want that happening, so you have this fiberglass layer, because the fiberglass can squeeze and grow. So let's say it's originally a foot of fiberglass, and you squeeze it down to 9 inches, or maybe it's 9 inches after you put the perlite in, squeeze it down to 6 inches, and it has that ability to move as the tank is taken out of service, if it has to be taken out of service. Now, keep in mind, most tanks are never taken out of service. They were built in the 60s and the 70s, and they're still in service today, never been taken out of service. Those tanks would have a bottom penetration, no internal tank valve, unless it's been upgraded, which would have to require you to take it out of service. In which case, if you did take it out of service, then you would have to install by code an internal tank valve. Let's go a little bit further and talk about the bottom of the tank. Here we have foam glass as the insulation. It has to be foam glass because it needs to withstand all the weight of this LNG. How much would you keep out? Let's say this tank happens to hold 42 million gallons of LNG. I use that number because that's the size of it's a typical size of a larger tank. For 42 million gallons of LNG, and LNG weighs about 3.5 pounds per gallon. And that's a rough number, 3.5 pounds per gallon. So you're talking about the order of magnitude of 42 million. Are you talking 3 times that? 42, let's say 50 million. Talking about roughly 150 million pounds of force that are being held, or downward weight that's being held by this foam glass Plus you have the weight of the metal that's associated with the tank itself. And that for the inner tank, you have a footing. For the outer tank, you have a footing as well. And you have to have hold down straps so that the tank doesn't bulge upward when it's pressurized and it's got no liquid in it. If you pressurize it, let's say it has a very little amount of liquid, but it still has a differential pressure inside the tank, well, you don't want it to bow upward. And you also have to have these straps for seismic reasons. So they're built into the calculation for seismic reasons. Now, these straps have to be carefully designed because as the tank shrinks, the tank moves inward. As the tank expands, the tank moves outward. So that has to be taken into account with the design. And the outer tank, which is made of carbon steel, also has straps attached to it. Let's take a look at what we have up here. You have a vacuum breaker. This is a vacuum safety valve. In the event the tank were to see a negative pressure, it could crumple like a beer can. And since we're in the LNG industry, I shouldn't say a beer can, so I'll say a soda can. So it'll crush like a soda can or like a water bottle. So to avoid that, you have a vacuum safety valve. If you ever see vacuum in this space, air gets sucked in. Now, before that ever happens, what's not shown here is there is cover gas, which is a gas line that goes to your tank that would feed gas into the tank before you see a vacuum, but at very low pressures. So let's say a tank normally operates at 1 psi and you get down to 0.1 psi. Well, that cover gas would come in and supplement your gas. If the pressure still goes down and you see a very slight negative pressure, this vacuum safety valve would open. And what about that frost heave that I was talking about? Well, you want to prevent this underground from freezing. And in order to do that, if you're attached to the ground, if you're in touch with the ground, you want to have heating cables in there. And these are your heating cables. And the way the heating cables are put, like this, conduit, 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 and you're running typically 3 number 12 wires through this conduit, and you're running voltage or power supply to those electric wires. Typically, it's 3-phase 480 volt. And I'm saying typically only from my experience of the facilities that I've been at. It doesn't have to be that voltage. But let's say this is an older system, and older systems had on-off thermostats. They come on, they come off. Well, what happens to the wire? The wire stretches and it shrinks, stretches and it shrinks. Why? Because it's hot and then it's cold, hot and it's cold. And that causes chafing, and it can cause the wiring to short out. So a lot of these systems have been converted to modulating voltage instead of on-off thermostats. And modulating voltage limits the amount of chafing because it limits the amount of high temperature, cold temperature, high temperature, cold temperature. Where do you measure your temperatures on the LNG underneath the tank? Well, you have other conduits that go this way, and you have thermocouples inside of here, or RTDs, resistance temperature devices, and these will tell you the temperature profile that's underneath your tank. Let's say you get a conduit that corrodes out or gets welded inside by arcing that occurs on your wiring that has now shorted out, and you can't get that wiring out. So let's say you lose this conduit, where you have to make up for that heat by adding additional heat to the adjacent conduits. And typically, they're not set up to only heat these conduits, so it's typical that your entire system has to be raised in temperature to make up for any losses of conduit. Now, if you're fortunate enough, you lose one conduit and you won't lose the second conduit. If you lose, is far away from that. Where it gets problematic is where 2 conduits adjacent to each other or 3 conduits adjacent to each other fail. And that becomes very difficult because then you have to come up with some creative ways to get heat into these conduits. One creative way is, instead of running wiring through here, if it's plugged or if the conduit is broken, you can put in one-way heat tracing wires in there. That has been one solution that has been used in some locations. Anything else we see on this? The only thing I can talk about, I didn't mention this here, the NRAFs. Remember we spoke about NRAFs being level gauges, and those are nothing more than a ball floating inside the LNG with a ribbon that comes up to a spool. And it's typical to have 3 NRAFs so that you can compare the 3 readings. And what you have to watch out is, when you do maintenance on your NRAFs, you have to reel up this ball before you close the gate valve to work on the NRAF. And the NRAFs are typically in what's called a stilling well. And a stilling well is nothing more than a tube, let's say a 6-inch or 8-inch diameter tube that has many holes drilled in it to avoid having waves. Let's say you're top filling and you're getting some agitation. You don't want this NRAF to be bouncing in here and wearing out your spool. You want it to be relatively steady. So that's why the stilling well is used. And you typically would have 3 NRAFs on a tank. This is nothing more than a closer picture of the configuration of how you'd have your heating system provided for a tank. Now, this is for tanks that are on the ground. There are some tanks that have a space between the bottom of the tank and the ground, and those tanks are set on piles and pile caps. So you have a bunch of piles in the ground, and then you have the tank sitting on top of that with maybe an air gap between, maybe a 2-foot air gap between the ground and the bottom of the tank. Maintenance of the heating system is extremely important. It is prudent to replace the heating wires before they fail. Condition monitoring is critical. If inspections reveal that the insulation is failing or chafing, a proper maintenance program should be implemented if one is not already in place. If the heating system has been seriously compromised, it is recommended to promptly contact the tank manufacturer on how to remedy the situation. To my knowledge, there is no way to replace underground tank heating systems that are not repairable. There are some methods of coming in from both sides with heat tracing, but there's no way, if, let's say, the conduit is pulled apart, to replace that conduit. If the potential frost heave is suspected, until a remedy is found, an MOC reviewed, and it must be reviewed and implemented. It would be prudent to perform a risk analysis and follow up recommendations from that risk analysis to make sure that you don't end up having frost heave taking place. In summary, for this event, your job is to monitor the system and to coordinate with management, engineering, and maintenance, and other stakeholders of the status of the heating system. These actions can prevent equipment from being damaged and prevent potential hazards. When we started off this presentation, I talked about a person that was killed on the job. It was my boss. And what went wrong? Well, a number of things went wrong. One of the key things was a lack of lockout tagout. This was when the distribution department was working with the plant, and in plant it is typical to use lockout and tagout. And in distribution department, it was at that time it was not a typical procedure. And what was happening at that time, this was a 48-inch gas main, and it went from a place where there was a stoppers installed. This 48-inch gas main went for quite a long distance, many blocks, to another location. There was no stopper installed, and this entire line was filled with nitrogen. And men were working here to remove a section of pipe. And there was another stopper here as well. Well, what happened is, because of the failure to lock out and tag out a 2-inch valve at the odorant station, the operator came out of the compressor building, saw that the valve that was normally open was closed, and he opened that 2-inch valve. That overpressurized the stoppers, blew the stoppers, and just at the time the crew here was removing this section of 48-inch pipe. So this pressure came down, blew this stopper here, and that nitrogen started flowing the into the opening. Now, something you have to realize about your lungs. What is a lung? It's a very high surface area. That's why it has all those air sacs. Very high surface area, semi-permeable membrane, which means that the gases will cross that membrane from a high concentration point to a low concentration point. So if you have 21% oxygen in your lungs and your hemoglobin is low in oxygen, the oxygen will go from your air part of your lung to your hemoglobin. But if it's just the opposite, let's say you breathe in a breath of nitrogen with no oxygen, the oxygen will leave the hemoglobin and go out to where the nitrogen is. So it'll actually extract oxygen from your hemoglobin. From your heart, from your lungs, the blood goes to your heart. Heart without oxygen content in the blood doesn't pump. Goes to your brain. Brain without oxygen content isn't conscious. So you can get one breath of pure nitrogen and just collapse. Well, that's what happened here. These men that were working in this opening started to collapse. Other men went into the opening, tried to pick them up and save them. They collapsed. My boss, who was at this location, got in his car, drove to this location, saw men in the opening, jumped in, and he collapsed. Unfortunately, where he collapsed, his face was very close to where the nitrogen and gas were coming into the opening. Of the 6 men that collapsed, 5 of them were revived. I can't speak to their cognitive ability after they were revived, but the 6th person, which was my boss, was taken to the hospital and did not survive. So that's the long and short of this lockout and tag out mistake. And I can't emphasize enough about how important lockout and tag out is. Today it's become extremely common, not only common, required to do lockout and tag out on all jobs in LNG plants. And I cannot speak for other companies, but I know all jobs that involve dealing with hazardous gases will deal with, or hazardous in general, will have a lockout, tag out procedure. It was about 50 years ago, I'd say, that this particular accident happened. This job was a joint effort between plant and distribution department personnel. At that time, it had been common for plant personnel to use lockout, tag out, but distribution personnel had not incorporated lockout, tag out into their procedures. It so happened that the distribution personnel wrote the procedure and thus did not incorporate lockout, tag out. The lockout tagout procedure should have been incorporated into the procedure. Besides lockout and tagout procedure, continuous air quality monitoring and alarming equipment should have been used on this particular job, especially since nitrogen is odorless. You can't tell if nitrogen is coming into an opening. The air we breathe is 78% nitrogen. Training on responding to a lack of oxygen incident was needed and was not performed. What often happens is when somebody collapses, other people go into the opening to try to help that person out without understanding that where the would-be rescuer can now also become a victim. And that has been very common. When a person is asphyxiated, another person jumps in to help that person, and that person becomes a second victim. Think of how much strength it takes to lift up a 200-pound person and help that person out of an opening if they're totally unconscious. It's like lifting 4 sacks of potatoes at once. In conclusion, LOTO, That's lockout tagout procedures must be used on all jobs where valve positions must be ensured during maintenance activities. Where the risk of asphyxiation exists, continuous monitoring equipment and alarming equipment should be used. Where the risk of asphyxiation exists, harnesses should be used along with a means of extracting personnel from a high-risk area. Self-contained breathing apparatus should be available on all jobs that have the potential for asphyxiation risk. All gas operating personnel require training on the effects of a lack of oxygen and how to respond to such a lack of oxygen accidents. Think of one of the things that happened at this job. Many of the people that went into the opening said they put a rag over their mouth or put the shirt over their mouth in order to not be overcome. That does nothing for a lack of oxygen event. It's a false belief, and that's why training is essential. Safety moment number 23. 2 men died and others were injured. The procedure was not followed. A 24-inch diameter gas main, newly installed, was being pressure tested, and the procedure was to put a cap on the end of the pressure test piping and then to strap it on using specially designed straps that were to be welded onto the pipe and onto the cap. There was a welding procedure associated with the welding, and over years, the welding became less and less uh, following the procedure, and then eventually this accident occurred. On the cap was 45,000 pounds of force. Now, the crews were used to installing a smaller diameter piping with much less force on the cap, and the welders were required to make a significant amount of welding, and over the years they did less and less welding, and then eventually during this job, the cap blew off. 2 men were standing on top of traffic plates. Those 2 men were killed on the job. As I stated, this crew had been used to installing smaller diameter mains, and the force on a cap is not linearly proportional to the diameter. It's exponentially proportional to the diameter. So let's say a gas main that was half that size. Well, that would have a relatively small amount of force on it, as you can see here, whereas a gas main that was 24-inch in diameter has a significantly larger force on it. Go even higher, and the force gets even larger. 36-inch main would be up here. The force on the cap, as shown here in a table form, and you can see the 12-inch main would be only 12,000 pounds, actually 11,300 pounds, whereas twice that size is not 22,000 pounds, but instead is 45,000 pounds. So knowledge of this is not something that was common knowledge on the job. Here's what happened on this job. Most of the earlier jobs were smaller diameter pipes. Each strap connection by procedure was to get approximately 7 inches of weld material with 3 passes on the weld. Over the years, welders became lax on details and put much less than 7 inches of weld material on each strap. Also, over the years, the welders only used a single pass to connect the straps instead of 3 passes. Due to the lack of weld metal, the straps ripped off, allowing the cap to blow off, which blew the plates off the opening, killing the 2 men that were standing on the plate. A lack of quality control resulted in no one checking on the work done by the welders. If quality control had been used, those welds would have been inspected and they would have been told to put the additional weld material and the additional weld passes on those straps. In conclusion, This accident was avoidable if the welders had followed the procedures. Two men needlessly lost their lives and others were injured. Procedures are not made to satisfy regulators or to satisfy management. They are made to reduce risk of accidents. Procedures are to be followed, and quality control of adherence to procedures is essential. Safety moment number 24, and this has a lot to do with engaging the brain before taking your foot off the clutch. A separate incident not related to this safety moment. After 9/11, I ordered that the entrance to the LNG tanks, where you could drive a truck to the LNG tanks, had to be chained off. And when I came there the next day, I saw a bicycle chain across two poles, and you could either drive through that chain because it was a bicycle chain, it was a very light chain, or you could drive around the poles. That's not engaging the brain. When I ask for a chain across the entrance, I mean so that a vehicle cannot get the into the inner dike area. And that's the kind of thinking that I would expect from any employee. But this is the kind of thinking that you have to develop as a culture. So this safety moment has to deal with winter happens every year, and we should expect cold weather. Event number one. The engineer reports to the chief engineer that 274 customers were lost gas service this morning. The chief engineer asked why. The engineer responded, "Well, it was cold outside." The chief engineer responded, "Unless it is colder than our design hour, that is never an acceptable excuse for loss of customers. We design for design hour. We know cold weather comes every year. It is the LDC's obligation to design the system to provide adequate supply to all customers down to the design hour. There's no excuse for losing customers because it's cold outside if it's not colder than the design hour." Winter happens every year. We should expect cold weather. Event number two. Synthetic natural gas peak shaving plant shut down on a cold winter day. The engineer reported to the maintenance superintendent that the filters supplying the naphtha feedstock froze up with ice like they do every cold winter day. The maintenance superintendent responded, "Unless it is colder than our design hour, that is an unacceptable excuse for a plant to shut down. If it is known that water in the naphtha supply freezes up the filters, freeze up every time it is cold outside, then install naphtha preheaters to avoid such freeze ups. It is the plant operator's obligation to ensure plant reliability, especially during cold weather when the plant is most needed." The follow-up to this was that naphtha preheaters were installed. Winter happens every year, so we should expect cold weather. The projection was that tomorrow would be the first design day the territory would have experienced in the past 20 years. That would be the coldest day in 20 years. The chief engineer ordered that backup diesel generators and diesel air compressors be shipped to every one of the 28 LNG facilities and propane air facilities to ensure their ability to produce send-out when needed if there was a power outage. None of the diesel generators or compressors started on that design day. Not a one. All of the diesel equipment was fueled with summer diesel fuel, which gelled up in the fuel filters. This was inexcusable. Winter happens every year. We should expect cold weather. Event number 4. A gas cooler intended to cool gas during summer months was used during the winter. The gas contained CO2 and water vapor. Because the water vapor condensed, it formed carbonic acid in the presence of CO2. The carbonic acid liquid droplets impinged on the piping elbow at high velocity. The carbonic acid eroded and corroded the pipe elbow, causing it to rupture and ignite. A crew of 6 people had just left the area to go to lunch when the elbow that they were working under had ruptured, causing a jet fire to engulf the area where they were working. Fortunately, they were out to lunch. Lesson learned: understand the consequences of improper operation of your equipment and also understand the process. Winter happens every year. We should expect cold weather. This is a story about a near-death experience. A steam trap pointing downward to the ground was stuck in the open position for months during winter operation. The open steam trap created a crater filled with hot water, which was surrounded by ice. Workers and supervisors walked past that crater for weeks, never giving it any thought. It was considered just another malfunctioning steam trap. One day, a general foreman and his crew walked by the crater. The general foreman slipped on the ice and slid into the hot water. The crew pulled the general foreman out of the water and quickly removed his hot water-soaked clothing. As they pulled the clothing off, his skin peeled off his body due to the burns. After an extended hospital stay, the general foreman survived. He survived the life-threatening burns, but was severely disfigured. Lessons learned. The above 5 events are only a few of the very many cold weather negative events that should have been prevented. Winter happens every year. Conscientious, proactive thinking is an essential qualification for all gas operating personnel. Always ask what could happen and what should be anticipated because cold weather preparations are essential. Training on employee expectations is important for safe operations and efficient operations. Employees will live up to your expectations. If you expect lackluster performance, that is what you'll get. If you expect excellence and follow up to get excellence, that is what you'll get. Before transitioning to talking about specific topics of LNG safety, I'm going to tell you about 2 accidents. One was the worst LNG accident, which occurred in 1944. The 1944 Cleveland, East Ohio explosion, which killed 130 people, was caused by inadequate safety measures in the gas storage facility. Engineers failed to address known risks, leading to devastating consequences. This event highlights the importance of rigorous safety protocols in industrial engineering. The explosion also brought attention to the role of corporate responsibility, the need for stringent safety regulations. It remains a cautionary tale about the ethical responsibility of engineers and corporations in preventing industrial accidents. Lessons learned, just to state a few of them, because there were many lessons learned. Containment needs to be suitable for minus 260 degrees Fahrenheit. Secondary containment is needed for LNG storage. Codes for storage of LNG were needed. This event was the impetus for the development of NFPA 59A. This shut down the use of LNG for the gas industry for approximately 20 years. Another gas LNG facility had not been built for a 20-year period. Another incident occurred in 2014, the post-purge accident that occurred in Plymouth, Washington. And as you can see, there's a tank that shows what looks like perlite spilled across the ground. And when this incident occurred, there was LNG spilling from a pipe, a small diameter pipe at the tank itself. Before we go into what exactly happened here, let me give you a little bit of purge technology discussion. There are different types of purges. There's diffusion purges where you put gas into, or put let's say nitrogen or some inert gas into a vessel, and it diffuses through the vessel. This takes a long time to purge. Then there's also displacement purging. Let's say we had a vessel that had a gas in it. We wanted to get rid of that gas, and we put a liquid inside. You get a diffusion purge. Now, of course, with LNG vessels, you can't put a liquid inside, but you can put a colder gas, which is much more dense, and that would allow a diffusion purge, or at least a partially diffusion purge to occur. And that is a much more rapid purging. Another method of purging is called pressure purging, where you pressurize a vessel or a pipe and then you depressurize it. Pressurize and depressurize it. And that brings the oxygen content within that pipe down over a period of cycles of pressurizing and depressurizing. The type of purge that was used in Plymouth, Oregon was the pressure purge method. Here's what happened. Inadequate purge of the regeneration system in the liquefaction area resulted in an explosion. A pressure purge was used. Shrapnel from the explosion punctured the outer tank of the LNG tank and broke a small line at the tank. Perlite and vapor leaked from the outer tank. LNG leaked from the broken pipe. The inner tank was dented but not punctured. This is an example of, it may not have happened the 20 times you did it before, but if they have an unsafe condition, one day that event could happen. And complacency can set in when people say, we've always done it this way and we've never had a problem. Always consider that there could be a risk associated with something, and so you have to understand the full ramifications of every action, even though it didn't explode last time you did the process. Now I'm going to transition to special safety-related topics for LNG. This is a series of generic safety moment topics. Special topics related to LNG. Know your wind. Know which way your wind is going. When you're at an LNG plant, every so often look at the windsock. See which way the wind is blowing. In the event you have a leak or some major spill or some event, you'll know which way the gases will be flowing and where to muster for a safety location. I was on one job where it was a portable pipeline, and the safety briefing was being read, and the person said, in the event of an emergency, we are to muster at this location. Tapped him on the shoulder, called him over, and said, maybe we should muster at the opposite location, which is upwind of the portable pipeline that we were working on. And he went out, reread the safety topic, and changed the muster location. Always consider your wind condition. This picture clearly shows why you should know your wind. In the event you have a spill, would you want to be on the right side of the spill or on the left side of the spill? Your muster point should be on the right side of the spill, not the left. Also, this shows that LNG vapors coming off of an LNG pool hug the ground. They do not rise. There are many people who think, well, natural gas is lighter than air, so the gas coming off of an LNG pool, the boil off, will vaporize and rise. But they won't, because they're so cold that they are heavier than air. LNG boil off becomes buoyant at about minus 150 degrees Fahrenheit. The vapor coming off of a pool of LNG is approximately minus 260 degrees Fahrenheit, which is denser than air at that temperature. Special topics related to LNG operation, a major caution. Nitrogen and also LNG vapors are odorless. So you cannot tell if you're in a oxygen deficient environment unless you're measuring for oxygen. So it's something to keep in mind. We don't often deal with vapor in a confined space or or large amounts of vapor in an open space, and we may not realize that we are in an oxygen deficient environment if we have an LNG spill or if we have a large nitrogen release. Another special topic that we have to be aware of is water hammers. They're called water hammers, even though they really should be called fluid hammers. And there are two different types of water hammers that we deal with. One is called a condensation water hammer. Consider a pipe that's operating with LNG in it, and it has a dead leg. And that dead leg is filled with warm LNG. Why is it warm? Because the LNG is at very high pressure. Let's say this is feeding a vaporizer, and this is a warm leg that goes to another set of vaporizers. Well, this warm leg has LNG in it at a warm temperature. Why is it warm? It's not moving, so it's maybe minus 200 degrees Fahrenheit instead of minus 260. Now all of a sudden, you have an emergency shutdown or some type of shutdown, and the pipe depressurizes. Here I just selected 40 psi gauge, and now this warm LNG vaporizes and leaves a long leg of vapor. Now you restart the plant, and it goes back up to 1200 psi. The vapor collapses and goes back into LNG, and as it does so, a very rapid, fast stream of LNG is heading to this dead end. When it hits the dead end, boom, there's a water hammer. That water hammer can be a spike in pressure that can cause this pipe to rupture or can cause this a valve at the end of this pipe or any other equipment to rupture and cause a large leak. So this is something to be concerned about when you're dealing with systems that have been pressurized and then depressurized and then repressurized. So how would you repressurize this to 1200 psi? Slowly. You bring up the pressure, you start the pumps on recycle, and you bring up the pressure slowly, which allows this section to fill up slowly. And then when it's totally up to operating pressure, you can then continue your operations. It's another type of water hammer, or I should say fluid hammer, that can happen. And that is the concept of the Joukowsky effect. And the Joukowsky effect is when you suddenly shut down the flow in a pipe. So let's say I have LNG or some fluid, any fluid, flowing in a pipe, and I have here, I put in a butterfly valve. And all of a sudden I close that butterfly valve. Well, this may be 1,000 feet of piping. We think of the mass of that fluid that's flowing, and all of a sudden this valve shuts, crash, you get this very high pressure spike into this area right up against the butterfly valve. That's not the end of the story. The Joukowsky effect then sends a pressure wave at the same spiked pressure all the way back to the source of where the LNG was coming from. So let's say this pressure spike was 1,000 psi. Well, that 1,000 psi spike, even though this may be operating at 200 psi, this 1,000 psi spike travels all the way back to the source of where the LNG was coming from. Now, that is if the pipe is totally rigid. If the pipe is not totally rigid, that pressure spike dissipates as it goes back. But depending upon how rigid that pipe is, there certainly will be a spike of pressure that goes back to the source of the LNG. So now you have this pressure spike, which I'm showing here as a double set of lines continuing back. Now that gets to the other end of the pipe and it goes back again. Now also what happens on the downside of the valve is you have a vapor bubble form. And that vapor bubble starts to slow down this LNG that's downstream of the valve. And what does it do? It then starts heading back to the gate valve, and boom, it crashes into this, I said gate valve, a butterfly valve is what it was. And that when it happens, you get that spike, pressure spike goes back again. It's a phenomena that very few people are aware of. But when you're designing valve closures, you have to design them not to instantaneously close. So they need to close in a manner that is slow enough to avoid this effect. Typically, plants are designed to operate where valve closures, especially on large piping, is typically 1 to 2 seconds per diameter inch. So a 30-inch pipe might have a valve closure that takes 30 seconds to close that valve, so that the closing of that valve does not cause that pressure hammer. The one place I would give you a concern is PERCs or ERCs, which are powered emergency release couplings. Those are fast-acting valves that are used on ship connections when you're offloading or loading a ship. And you have to do some calculations to make sure that the timing of that PERC valve closure is not such that it's going to cause damage either on the plant or on the ship. Here's a caution about when you're reading low pressures. Be careful, flowing piping may give you false readings when you think you're measuring tank pressure and you're actually measuring on a line that goes to the tank. Well, if that tank is flowing and it's low pressure, you can be getting a false reading. Ideally, if you want to measure tank pressure, you measure it at the tank itself. And there'll be a penetration at the tank itself on a line that has no flow in it. Also, you have to be aware that on low pressures, you're very sensitive to having a kink in the pipe or maybe having a liquid in the pipe. A liquid trap would certainly give you a false reading. Also, you have to be aware that reading your low pressure is dependent upon the location of where you're reading it. If you're reading a tank pressure, you want to be referenced to an inside and outside pressure. You don't want to be inside a building where the building itself is pressurized and you're reading that gauge inside the building unless it's a transmitted pressure. But let's say it's cold outside and the operator is reading a gauge and he goes into a building and lets the hose be extended to the where he's reading. Well, that building may be pressurized or either negatively or positively pressurized, and that can affect your reading. These are things you don't typically think about, but what I'm trying to encourage is thinking of all the things that can happen. Continuing on special topics related to LNG operations, realize that freeze burns can be very serious. They may result in injury, amputation, or death. And I know of at least one incident where the person died when a valve ruptured and he was covered with LNG. I experienced a freeze burn once on this finger, and I was making up a fitting. I had gloves on, and I was almost there, and I knew I was getting burned, but I said, "I got it," and I got the fitting, and then I took the glove off, looked at my finger, and it looked kind of strange, and it was burnt, and he said, "Let's wait and see what happens." It started getting dark. It started changing color over the days, and then finally I went to the doctor. Doctor said, "You're lucky you didn't get it on both sides of that finger, because you've done some damage." And it took a number of weeks before that freeze burn was totally healed. But that was a little bit of stupidity because I knew I was getting burnt and just kept make up that fitting. I could have stopped the operation and then change changed the mode of shut down the source and then continued to make up that fitting. Engage the brain before taking your foot off the clutch. Now let's talk a little bit about siting an LNG plant. And this has to do more with design engineers understanding how to site an LNG plant rather than how to operate an LNG plant. But operators should at least be aware of this information. 49 CFR Part 193 references NFPA 59A. NFP 59A is a consensus code, which means you are not required to abide by NFPA 59A, except for the fact that it is referenced by 49 CFR Part 193. That means that because of Part 193, NFPA 59A is required by LNG operators to be used as a code of conduct for, or as a code of operation for LNG facilities. This is a part in NFP 59A. Let's read it. And I'm going to be using the English units. It says a property line at ground level that can be built upon for ignition of a design spill. And it's important that we talk about what a design spill is. And what it's saying is that when you build a plant, you cannot have more than 1,600 BTU per hour per foot squared at a property level, at a property line at ground level that can be built upon for ignition of a design spill. Let's say at your property line starts a lake. Well, at the property line starts a lake that cannot be built upon, and that would, of course, you'd have to have really a legal designation as to what you consider what can be built upon. But this is a requirement, radiant heat flux limits to property lines and occupancies. It also says that the nearest point located outside the owner's property line at ground level that at the time of plant siting is used for outdoor assembly by groups of 50 or more persons for a fire in an impound area. That's note B. So this is an impound area as designated by 5.3.2. Then the next part says 3,000 BTUs, and this is the nearest point on the building or structure outside the owner's property that is in existence at the time of plant siting and that is used for assembly, education, healthcare, detention, and correction, or residential occupancy for a fire in an impound area. That's B and C. B and C is the requirement for the impound area of 5.3.2, and C is CNFPA 101, Life Safety Code, etc. Then you have 10,000 BTUs at a property line at ground level that can be built upon for a fire over the impound area. This is point B. So what's the difference between an impound area or a design spill? Well, the impound area is your secondary dike. It's the, let's say, a single containment tank. It's the dike around the tank itself. So that's quite a large fire that we're talking about. And these are really for impound areas. And this is for a design spill. And a design spill is very much different. It's a very limited amount of LNG in most cases, unless you have a bottom penetration that has a guillotine cut and there's no internal tank valve. So we'll talk about that. Now, keep in mind that I'm going over this at a very high level. When you're actually siting a plant, there are lawyers involved, and the FSMA staff is involved, DOT staff, PSC staff, and many other people involved that will be making the interpretation of what the code is specifically saying. So I'm giving you a high-level overview. When we talk about a design spill, there are essentially three cases. One is a design spill of, let's say, a single containment tank that has a bottom penetration. And one scenario is there is no internal tank valve. The other scenario is there is an internal tank valve. And the other is for a full or double containment tank. So the three scenarios I'm going to be talking about is a single containment tank with a internal tank valve and without an internal tank valve. And then the third case would be a full or double containment tank. Okay, design spill. A calculation method is shown here, and it assumes that you start off with a fully right to the brim filled LNG tank, and you have a guillotine cut of a bottom penetration. And for the first case, we're going to look at with no internal tank valve. And you have a formula for the flow rate of LNG that comes out of that tank. And that formula is to be used until the tank is fully emptied or until there is zero differential pressure acting across that bottom inlet and the outside. So that is a total emptying of the tank into your dike area, and that's that would be your design spill for a tank without an internal tank valve. For a tank with an internal tank valve, and it should say with internal, here it is, with internal tank valve in accordance with this, you have the same calculation. However, that calculation is limited for a period of 10 minutes. Now, you can actually get a waiver to go below 10 minutes, but you have to be able to prove that your equipment is such that it would shut down quicker than 10 minutes. I don't know of anyone who has been pursued that ability to go below 10 minutes. So essentially 10 minutes is given as your design spill for tanks that have internal tank valves. And the third case is for a full or double containment tank. And for that, the design spill is zero. There is no design spill that you have to design for heat radiation calculations. Now, so far we've spoken only about tanks that have bottom penetrations. What about the tanks that don't have bottom penetrations but have internal tank pumps? Well, for those tanks, we have similar requirements, a guillotine cut of the piping. And for those tanks, we're going to look at the maximum flow from any single line that could be pumped into the impound area with the container withdrawal pumps delivering at full rated capacity as follows. For 10 minutes if surveillance or shutdown is demonstrated and approved by the authority having jurisdiction. For the time needed to empty the full container where surveillance or shutdowns is not approved. So a prudent plant siter would certainly have surveillance and shutdown capability built into their plant, and the design spill would be for a guillotine cut at maximum flow from that tank. So if you have internal tank valves, talk about a guillotine cut, maximum flow from those internal tank pumps, and that maximum flow would be for a period of 10 minutes, and that would be your design spill. For impound areas serving only vaporization or process areas for 10 minutes or shorter time based on demonstrable surveillance of shutdown provisions acceptable to the authority having jurisdiction. And so that gives you your design spill for single containment tanks, double or full containment tanks, tanks that do not have bottom penetrations. That's what we've covered so far. Let's move forward. This is just a Google Earth snapshot of a set of LNG tanks. And as you can see, looking at the picture, there is a impound area here, and this would be for your design spill. There's also a dike area, and this would be for your full release of the LNG. And this would be what was called that subscript B, and this would be what is called that subscript A. So this is your design spill, and this is your impound area spill. This would be intended for an entire tank release, and this would be designed for your design spill. Other regulatory codes that you must abide by: 49 CFR Part 193, which references NFPA 59A. Although NFPA 59A is a consensus code, it is mandated because it is referenced in Part 193. And also, both of these codes give reference to numerous, I mean many, many other codes. So you have to go through all of the references and see the codes that are required for both Part 193 and NFPA 59A. When siting an LNG plant, there's also a requirement to meet the code requirements for vapor concentration at the property line. And that vapor concentration is given as an average concentration of methane in air of 50% of the low flammability limit does not extend beyond the property line that can be built upon in accordance with, and he lists what models to use on that. And that is for a design spill. This slide shows isoplets for a design spill. Now recall, we talked about two types of spills. A design spill, which is a limited spill. In most cases, it's a limited spill unless there's no internal tank valve. And a full dike spill is the full impoundment area being filled with LNG. So there are two different types of spill, and this is asking you, can this plant be built on if this is the isopleths for a design spill? And take a look at it, and we see there's 16,000 BTUs outside the property line. That's 6,000 BTU per hour per foot squared. And the question now is, can this be built upon? Can this LNG plant be built by code? And the question really determines, is this land that can be built upon? If it's land that can be built upon, then this cannot be cited as acceptable, meeting code requirements, because you could build a building here, you could build a building here, etc. Now this slide shows this same exact isopleths as the earlier slide. However, this is not for a design spill. This is for a full dike impoundment fire. And what does the code say about a full dike impoundment fire? It says that the 3,000 and the 10,000 BTU limits are within the property line, so that's acceptable. But what about the 1,600 BTU per hour per foot squared? Well, for a design spill, it talked about land that can be built upon. But for a full impoundment spill, it talks about there being a facility or a building of public assembly where 50 or more people can exist at the time of siting. So if this is vacant land, then yes, this would meet the criteria for siting this LNG plant. But if this has a place of public assembly of 50 or more people in existence at the time of the siting, then no, this would not be acceptable by code. So far, we've spoken about radiation, thermal radiation from fire. Now let's talk about gas concentration from a spill. Now, this is based on gas concentration. Can this plant be built if this is the gas concentration for a design spill? And if you look at it for a design spill, where is the 50% LEL level? It's right here within the boundary line. So yes, this plant can be built based on the design spill vapor concentration. Now, I have heard that There may be some changes in the code that have been made recently, so I can't say this definitively, but for the copies of the code that I have right now, this meets that criteria. It shows lines of constant gas concentration for a spill that is a full dike impoundment spill. And this line is 100% LEL. This line is 300% LEL. This line is 1500% LEL. Now you might say, how can you get 1500%? Well, how can you get 300%? Well, what is 1 LEL, or 100% LEL, I should say? Well, that's 5% gas. So 300% LEL would be 15% gas. 1500% LEL would be 75% gas concentration. Is this allowed by code? The answer is the code is silent about a full dike impoundment spill and gas concentration. So this is really not a requirement associated with the code. So we've talked about thermal radiation requirements for getting a permit and vapor concentration requirements for getting a permit. That doesn't guarantee that you will get a permit, nor does it guarantee that you will get an operating permit after you get a permit to build. You can invest millions or billions of dollars and be denied a permit to build or to operate. Take, for instance, the more important concerns of public and political opinion. These can be stronger reasons than technical reasons why you cannot obtain an operating permit. Look at Shoreham Nuclear Power Plant. Billions of dollars were spent on building that plant, and it got up to 5% power and then was shut down. District gas tanks in Staten Island. They were totally built, ready for operation. The commissioning cargo was en route to that import terminal when the operating permit was pulled for that plant. And those tanks still stand today, 50 years after they were built. And they never saw a drop of LNG. What happened? Public opinion was strong against the tanks, and that pushed political opinion, which then caused the removal of the operating permit from that plant. Geysering is another thing you need to be concerned about. Let's say you have a horizontal leg and a vertical leg that's filled with LNG. And heat leak into that LNG causes bubbles to form. Once bubbles form in this vertical leg, what happens to the pressure at the bottom of the vertical leg? It becomes less. Why? Because the bulk density of this liquid is less, and therefore all of this liquid in here starts to see a lower pressure. And once that starts to see a lower pressure, it generates vapor, and this is an accelerating event that can push that vapor and liquid out of the pipe at a very high velocity, which can cause thermal stresses at the connection point at the top of that pipe. Thermal expansion and contraction. Stainless steel contracts about 2.5 inches per 100 feet. And that's a rough number that I looked up, and 2.5 inches per 100 feet for a temperature change of about 320 degrees, which would be ambient temperature down to minus 260. So that you have to take into account using either a bellows or expansion joints. This is an expansion joint here. It's where it allows the pipe to flex. So you'll see these in many locations along a run of piping. Or you could have expansion bellows that allows the bellows to contract and expand as needed to avoid overstressing the piping. Over and under pressure protection is essential for all tanks, especially large tanks. And if you look at here, we're showing an under protection or vacuum breaker protection, and we've spoken about that already. And here we're showing an overpressure relief valve. Earlier, we've mentioned the need for having TESV, that's thermal expansion relief valves or safety valves. TESV is thermal expansion safety valves. Now, here's a thermal expansion safety valve. Now, we should have one here as well, unless we put in administrative procedure that forces this valve to be always in the open position. So this is a lock open valve, and this valve would be a lock closed valve. So administrative mechanisms can be used to avoid having to put an excessive number of relief valves on a plant, such as making this a lock open valve. A lock open valve is treated as a straight piece of pipe. Thus, this section of pipe is being protected by this thermal expansion valve. I earlier mentioned a ERC or PERC. That's emergency release coupling or powered emergency release coupling. And what it is two ball valves as shown here, and a release coupling. In the event a ship drifts off the berth and you're loading or unloading a ship, you want this to break away rather than rip the arms off of the berth. So if the ship moves too far of a distance away from the berth, or if a emergency relief valve button is pressed, and not emergency relief valve, emergency release coupling button is pressed, this will activate. These two ball valves will shut, and as soon as they shut, this release coupling will release this section from the rest of the loading arm. I mentioned this earlier because these are quick acting. They typically actuate in about 15 seconds time, and you have to make sure that that timing is not such that it would cause a Jaworski type water hammer or fluid hammer, I should say. This picture is shown just to let you know that there are failure modes for valves. In other words, if you have a loss of air or a loss of electricity to the ESD solenoid associated with that valve, the valve will fail in a certain position. And that valve can be a fail open, could be a fail closed, could be a failed as is, could be a failed at a fixed position, whatever the design engineer designs it to be. But operators and engineers should be aware that all of the automated valves in the plant have fail type positions: fail open, fail closed, fail as is, etc. Keep in mind, there are many types of hazard detection pieces of equipment in a plant. You can have an oxygen sensor. You can have a fire detector. This is a portable gas detector. This is a fixed position type of gas detector. This one happens to be an open path gas detector type that will look across a large area, let's say across 100 foot of plant area, and look for gas leaks that might be occurring somewhere within that 100-foot zone. And there are many other types of hazard detection devices within a plant, cold sensors, etc. Smoke detectors are also used in LNG facilities. This is an ionization type smoke detector. It's the type that you'd buy in a Home Depot. It's a relatively inexpensive. It has a radiation source, and alpha particles are transmitted from one point to another point. Those ionization particles, really alpha particles, which are ionize the air which causes electrons to flow between these two plates. And as smoke enters this area, it neutralizes the ionization of the air that occurs between these two plates, therefore changing the amount of current that is being fed between these two plates. And microprocessing is used to interpret that, and then it will give a signal to alarm if smoke is entering the area between the two plates. And there are photoelectric smoke detectors, and this would have a light source, which is powered, and a receiver. And it would have a receiver that's at 90 degrees. Now, this receiver would not receive any light unless particles of smoke were to come in here and reflect that light. Now, the negative part of this is dust or debris, let's say any kind of a dusty environment could certainly also trigger this type of smoke detector. But this light that is received by this sensor only occurs when some kind of a reflective material comes into this area. And that reflective material would be smoke. So smoke does reflect a certain amount of light received by this sensor. The smoke alarm goes off. Safety requires that the operators have a certain amount of understanding of thermodynamics. This happens to be a pressure enthalpy chart for methane, and it shows a saturated liquid line, a saturated vapor line, superheated vapor area, a subcooled LNG area, and an area where there's a mixture of LNG and LNG vapor. And we're not going to get into this thermodynamics. I have multiple courses that go into thermodynamics, but it's just a slide to show you that safety requires a basic understanding of the thermodynamics of LNG. Here's a thermodynamics question for you. Let's say I have steam rising from a location and I spray onto that steam cold water. Let's say I spray 100 gallons of cold water onto the steam, and then I collect the water that landed on the ground, and I find 110 gallons of water on the ground. Where did the extra 10 gallons come from? This cold water condensed the steam. And that's exactly what happens in a recondenser. If you have a recondenser in your plant, you are condensing superheated bog using cold subcooled LNG. This is a sketch of a recondenser. Superheated vapor comes into the recondenser. It cools down to saturated vapor, then condenses to liquid. And how does that happen? We have subcooled LNG being sprayed over it, and perhaps there's a contact mesh in this vessel where they come in intimate contact between the vapor and the subcooled liquid, and what falls to the bottom is liquid LNG, which is a combination of this subcooled LNG and the condensed vapor. Looking at this on a pH diagram, we could see the LNG became subcooled by pumping it to a higher pressure. Typically, it's about 60 to 70 psi gauge, and that subcooled LNG has injected in it some superheated vapor. So it cools down the vapor, and that superheated vapor then gets to be saturated vapor. Then it condenses to LNG, and it ends up at some point where there's still some subcooling, and it then goes to a second stage pump and goes to the vaporizers. So how is the LNG made subcooled? By pumping it. How is the superheated vapor condensed? By coming in contact with the subcooled LNG. And the end result is a slightly subcooled combination of the initial LNG that was pumped plus the vapor that was cooled and then condensed. Safety requires an understanding of gas interchangeability and an understanding of LNG weathering. FERC developed a white paper, and the white paper applies to the majority of the United States. There are some areas where there are extremes in gas composition, but for most of the United States this covers, and that is that the send-out gas must have a BTU content maximum of 1,110 BTUs per standard cubic foot, a WABI number, also called WABI index, of 1,400, and that's a unitless number. A WABI number that is within 4% of the historic WABI number for the territory that's being served. And the WABI number is a unitless number that is nothing more than a higher heating value divided by the square root of the specific gravity of the gas. And the specific gravity of the gas is nothing more than the density of the gas at STP divided by the density of air at STP. The total amount of inerts in the gas being sent out must be less than 4%, and the maximum amount of heavy hydrocarbons, that's C4 plus hydrocarbons, must be 1.5%, no more than that 1.5%. LNG that's stored in an LNG tank will weather over time, and its composition will change. And that is because the way LNG weathers is that its most volatile gases preferentially boil off. That's not sequentially, that's preferentially. When I say preferentially, it means like, let's say you had a tank that had methane, ethane, and propane. All three of those will boil off, but the methane will boil off at a much faster rate than the ethane and the propane. And that's because the methane is more volatile. If nitrogen was in there, then the nitrogen would boil off preferentially more than even the methane. But let's talk about most tanks which do not have nitrogen in the content of the tank. So you'll end up with the methane boiling off preferentially. And when that happens, you're left with more ethane and more propane left behind. So what does that do? It increases the higher heating value over a period of time, and it also increases the WABI index. So to show that, I made this Excel spreadsheet, and I put the number of weeks shown here, and I show an inventory going, and I selected a concentration of mostly methane, but it included 5% ethane, 1.8% propane, and over a period of time, I see the higher heating value increasing as the tank weathers. And I see the WABI number also increasing as the tank weathers. On the next slide, we'll show the remaining weeks of the year for this Excel spreadsheet. Here, looking at the remaining weeks of the year, you see that the higher heating value is continuing to get higher and higher. And here you see that the WABI index is continuing to get higher and higher. And at this point, the gas is that LNG is no longer interchangeable to be sent out because it has over 1,400 BTU, WABI number of over 1,400. And there's no units associated with WABI index or WABI number, whichever you choose to call it. And in order to send out this LNG, you'd have to either mix it with a lower WABI index LNG, or you'd have to stabilize it. Typically, stabilizing is done using nitrogen for stabilization gas. But keep in mind, you have the limitation of no more than 4% inerts in your gas. Relieving pressure in a plant or venting or flaring is very important. Venting is often performed, certainly at the relief valves on the top of the tank. But if you need to vent gas from the plant process, you typically would heat that gas up to a temperature greater, typically warmer than minus 50 degrees. Because remember, gas becomes buoyant at minus 150 degrees. Colder than that, it's heavier than air. So you don't want to vent gas and have it come back down to ground level. You want it to dissipate into the air. Another method, the more popular method of getting rid of gas that has to be vented or has to be relieved from the plant, depressurized, is to flare it. This shows a set of ground flares, and there are different types of burners shown here. I could recognize this burner as being an Invar burner, and this burner as being a local burner. Logo burner is what it's called. And there are different types of burners that are associated with ground flares, and there's also elevated flares, and you've seen those many times by petrochemical plants, and they would be a flare on the top of a stack. Myths are a common concern in LNG facilities. Myth number one, LNG vapor is nothing more than natural gas, which is lighter than air, which will harmlessly dissipate by rising into the air. And that's typically what PR people will say about boil-off gas. However, it is known that LNG vapor is heavier than air until it warms up to about minus 150 degrees Fahrenheit. Myth number two, Joe was a hero because he stopped that LNG leak. Quite often, if Joe had followed proper procedures, the LNG leak might not have occurred in the first place. Myth number three, if I stay out of the immediate area of combustion, I will not get burned. Burns can come from radiation energy, which extends well beyond the area of combustion. Myth number four, we can smell gas, so if there is enough gas for a fire, we will smell it first. Not true. LNG vapor is odorless, so you may not smell anything while in a gas leak. Myth number five, it says, if it's on fire, I will see it. On a sunny day under certain conditions, a natural gas fire may be nearly invisible. Certainly, hydrogen fires are very much invisible, but a natural gas fire may also be nearly invisible. I'll give you, for instance, there was a job where we were trenching over a gas main, and there was a leak on the gas main and caught fire. And the backhoe operator grabbed a bucket of sand, dumped it on the fire, and it looked like the fire was out until you walked over the trench and realized the fire was still ongoing. All that the sand did was give the fire a very flattened out uh, profile. What it was now the sand was acting like a spreader of the natural gas. So there was a small fire above the sand layer that was still on fire. So if it's on fire, I will see it is not always true. Myth number six is a very serious myth. If I put a rag over my mouth, I can go into places that do not have sufficient oxygen. I remember when I interviewed the people who were involved in the incident where the people were overcome by nitrogen and natural gas. They put their T-shirts over their face before jumping into the opening, thinking that that would protect them in this oxygen deficient environment. Well, obviously it didn't. Myth number seven. A heat burn is more damaging than a cold burn. The fact is that both burns can be very serious. Both heat and cold burns can be flesh damaging and life threatening. Myth number eight. It didn't happen last time, so it won't happen now. And this is a serious concern because it leads to complacency. Today is the first day of the rest of your life. Live it safely. I one time visited a operator who was unloading an LNG tanker truck, and I went down to the tanker truck area, and I needed to speak to this operator because his performance was less than satisfactory. And there he was sitting down. The truck was unloaded, and he was thumbing through a newspaper. I said to him, "You should be watching the operation." He says, "I've unloaded thousands of these trucks. Nothing ever happens." And that's where I had to take corrective action and say, your job is to be out there attentive to what's going on. And, I had to take corrective action in that case. But today is the first day of the rest of your life. Live it safely, not only for yourself, but for your fellow operators. I'm going to be wrapping up. And before I do that, I want to go over some basic safety that must be your highest priority. Safety is your responsibility. It's not the responsibility of a safety director of course, he's got responsibilities there, but safety has to be every operator and every engineer's responsibility. We have to be aware and cognizant of hazards to personnel, wearing protective clothing, personal safety equipment. Three common concerns associated with LNG and LNG vapors are the LNG vapors are flammable. The LNG itself is not flammable, but the vapors are flammable when mixed with air, mixed with oxygen. LNG and its vapors are cold. Breathing in cold LNG vapor can blister your lungs. Breathing in cold LNG vapors, aside from it being cold, is a lack of oxygen, which can asphyxiate. It displaces air, which can asphyxiate. So the three concerns are flammability, its temperature, and its ability to displace air. Now, I'm going to give you some brain teasers. I'm not going to give you the answer to the brain teasers because there could be many answers, but it's something for you to consider and contemplate and think about all the scenarios that could be happening. It's 2 a.m. in the morning, and it's always 2 a.m. in the morning when bad things are happening. Outside temperature is 0 degrees Fahrenheit, and the phone goes off. You pick up the phone and find out that it's not important. You send out gases in progress, and it is needed to avoid a natural gas supply shortage. LNG storage tank pressure is steadily rising. It's 1.2 psig at 2 a.m. in the morning, 1.5 psig at 2:10 in the morning. You maximize your boil off compression to remove as much boil off as you can. But the pressure keeps going up. It's now 1.7 psig and it's 2:20 a.m. in the morning. The tank pressure is still rising. Your concern is the tank relief valves are going to lift. What could be wrong? That's for you to consider and ponder. After all we've gone over and discussed in this lesson, you should be able to come up with several scenarios that could be at it. Brain teaser number 2. It's 3 a.m. in the morning, 0 degrees Fahrenheit. Send out is in progress and needed. Tank pressures have been unusually high all day. The outside operator reports a cold spot at the base of tank 1. What do you do? Brain teaser number 3. It's again 3 a.m. in the morning, 0 degrees Fahrenheit. Send out is in progress and is needed to supply customers. A ship is unloading and tank pressures drop rapidly. 1.7 psi at 2 a.m., 210, 1.4 psi. You stop compression. It's now 220 and down to 1.1 psi G. Now, when I say PSIG, you realize we're talking about differential pressure and it's still dropping. What could be happening? When I say differential pressure, I'm talking about the difference between the tank pressure and the outside barometer. But I didn't say that to give you any kind of a direction to go in. You got to consider what could be happening in this very short time frame that the pressures are dropping so quickly. Safety brain teaser number 4. You have an emergency condition. It's 3 a.m. in the morning, 0 degrees Fahrenheit. Send out is in progress and is needed. You have 4 submerged combustion vaporizers online. The alarm log lights up and an ESD occurs. The ESD appears to be due to gas alarms. Water has sprayed over much of your vaporization area. Gas readings were high, but they're now decreasing, but they were significantly high when the ESD occurred. What could be happening? Think about this. A hint there is that water was sprayed over much of your vaporizer area and that you're using submerged combustion vaporizers. But there are a number of scenarios that this could be related to. You got to think it out and see what ideas you come up with. Brain teaser number 5. Again, it's 3 a.m. and 0 degrees Fahrenheit. Send out is in progress and is needed. An ESD occurs. Your outside operator confirms that you have 10% gas in air in your WEG expansion tank. Remember, WEG is water ethylene glycol expansion tank. So you obviously have vaporizers that use hot WEG that come from the boilers, go past your WEG expansion tank, go into your vaporizers and then back to the boilers, etc. And now you have gas in your WEG expansion tank. What could be happening? What action should you take? Why do you think this happened? These are questions that you should be able to answer after having seen these safety moments. And this is my last slide. The most crucial intention of this document is to give you some examples that you need to start your study on how to continue making liquid natural gas industry safe and reliable. This is the start. This isn't the all with everything. This is only the beginning because your career has to be one of continuous learning, continuous improvement. The image to the left is placed here as a reminder that every one of us has someone who loves them and needs them to come home at the end of their shift. Your coworkers need to come home at the end of their shift. Your neighbors that are in the area where your plant is need to be able to come home at the end of their day. The reliability is also related to safety because if the LNG plant cannot send out when needed, the consumer public may be at risk of losing gas service during the worst possible weather, the coldest weather. This would put the public at a severe health risk. Engineers must ensure that the LNG facility design, planning, operation, and maintenance help assure safety and reliability. This will help ensure that everyone comes home at the end of their shift and that gas is supplied when needed to the end use customers. And that picture happens to be of my granddaughter.